Hey there. Before we drift into the strange and beautiful world of strings, let me ask you a small favor. If you're watching this while lying in bed, headphones on, the lights dim, tell me what time is it where you are right now, and what city are you in? I love seeing how far across the universe this finds its way, so drop it in the comments, and let's begin. The story you're about to hear is not the story of planets or stars, not the tale of galaxies or even atoms. It's the story of something far smaller, something so small, so delicate, so deeply hidden, that for most of human history, we didn't even know to look for it. It begins, not with a bang, not with light, not with matter, but with a question. What is the universe made of? Not just what we see, not just particles, but the foundation, the code, the rhythm beneath the silence. For centuries, science has searched for the smallest building blocks of nature. Ancient Greek philosophers spoke of indivisible atoms, the smallest units of being. Later, Newton gave us forces, Maxwell gave us fields, Einstein gave us the curvature of space-time, and quantum mechanics. It gave us uncertainty, probability, and strange behaviors too weird to believe. Yet, none of these alone gave us everything. Gravity refused to play nicely with the quantum rules. Particles seemed point-like, but mathematics broke down when we treated them as such. At the tiniest scales, tinier than atoms, smaller than protons, even beyond quarks, our theories fell apart. The universe began to whisper something we weren't ready to hear. But maybe, just maybe, particles are not points. Maybe they're strings. Tiny, vibrating strings. One-dimensional filaments, so unimaginably small that they thread through space like notes on a silent violin. And just like violin strings, they vibrate. And their vibration is what gives rise to everything. The string vibrating one way becomes an electron. Another frequency, a photon. Change the tension, the length, the motion, and the universe reshapes itself. In this vision, all particles are not different kinds of matter, but different songs played by the same string. This is the idea at the heart of string theory. A theory that dares to unify all forces of nature, gravity, electromagnetism, the nuclear forces into one majestic framework. A theory that says space-time itself might not be what we think, that dimensions might curl and loop beyond our perception, that the multiverse may not just be possible, it may be necessary. But like all grand ideas, it began humbly. Not in a lab, not in a telescope, but in the scribbles of chalk on dusty blackboards. Physicists hunting for consistency, trying to tame infinities, trying to understand the violent birth of the cosmos, and the quiet laws that guide it still. Tonight we trace the path of string theory, from its origins in the attempts to understand the strong nuclear force, to its rebirth as a theory of everything. We'll pass through quantum foam, hidden dimensions, branes and black holes, and even the echoes of creation itself. Let's start at the beginning. Not the beginning of time, but the beginning of confusion and clarity. In the 20th century, two great pillars of physics emerged: quantum mechanics, unpredictable, strange, and yet stunningly accurate in the small, and general relativity, smooth, elegant and majestic on the cosmic scale. But they refused to speak the same language. Try to unite them, and the math collapses. Equations break, infinities pop up where there should be answers. This became painfully obvious when physicists tried to describe gravity at quantum scales. General relativity works beautifully for black holes and galaxies. Quantum mechanics rules the world of atoms. But what happens inside a black hole, or at the instant of the Big Bang? That's where the clash becomes unbearable. We needed a theory that could do both, that could speak the language of probability and curvature, and that's where the idea of strings tiptoed onto the stage. In the late 1960s, physicists weren't thinking about quantum gravity at all. They were trying to understand the strong nuclear force, the glue holding atomic nuclei together. A man named Gabriele Veneziano stumbled onto a mathematical formula that matched experimental data beautifully, but no one really understood why. Then others like Yuichiro Nambu and Leonard Susskind looked deeper. They realized this formula described the behavior of vibrating strings, not particles but strings. It was a totally different way of thinking. At first, no one thought it was more than a curiosity, but as the math yokes, something strange happened. Gravity appeared. Uninvited, unexpected, but there it was. String theory, without even trying, produced a particle with the properties of the graviton, the theoretical quantum of gravity. Suddenly, this wasn't just about the strong force. This could be the theory physicists had been dreaming of, a unifying thread tying all forces together. one framework to describe everything: particles, fields, space and time itself. But there was a price. String theory only worked in 10 dimensions, not 3 of space and 1 of time, but 9 of space and 1 of time. Where were the others hiding? The answer came from a concept called compactification. Maybe the extra dimensions are curled up so tightly we can't detect them, like a garden hose seen from far away. You only see the long stretch, not the tiny circular cross-section. At our scale, the universe looks 3D, but on the tiniest scales there might be more. And those tiny shapes, those curled-up dimensions, aren't just decorations. They determine the physics we observe. The types of particles, the strengths of forces, the nature of matter itself, all encoded in the geometry of these hidden dimensions. This led to stunning mathematics. Calabi-Yau manifolds, branes, dualities, supersymmetry, each piece unlocking more layers of the theory. Each equation a step closer to the full song of the cosmos. And yet, it's incomplete. String theory is still a theory. Unproven, elegant, mysterious, but rich enough to dream through, to imagine. What if the universe really is made of music? As we move forward, we'll explore those hidden dimensions. We'll ride the ripples of strings. We'll dive into M-theory, black holes, and even the edge of space and time. But for now, let that first idea settle in, that everything might be the result of vibration, and that we are, quite literally, made of song. The music of matter, how strings make particles. If everything is a string, then everything is a vibration. And if everything is a vibration, then everything is music. Not music we can hear with ears, but a deeper rhythm, a structure of oscillations that ripple across the smallest scales of reality. The physics of existence, performed in silence. To understand how the universe takes shape from these invisible strings, we need to abandon the idea that particles are points. For most of modern physics, particles were treated as zero-dimensional dots, infinitely small, infinitely precise. But when we try to describe their behavior at incredibly high energies, the math breaks. We find infinities where there should be answers. Equations collapse under their own weight. String theory proposes something radical. That particles aren't zero-dimensional, they are one-dimensional. Tiny loops of vibrating energy, minuscule strings that pulse and twist and oscillate through space. These strings can be closed, forming a loop like a rubber band, or open, like a thread with 2 loose ends. Their vibrational modes aren't arbitrary. Each mode corresponds to a different property, different mass, different charge, change the way a string vibrates, and you change what kind of particle it becomes. An electron isn't fundamentally different from a neutrino. It's just a different song, a different vibration played by the same kind of string, and the properties we measure, mass, electric charge, interaction strength, are determined by the frequency, amplitude, and shape of that vibration. Imagine a violin string. The way it vibrates depends on its length, its tension, its material. In string theory, those parameters are determined by the geometry of space-time, by how the extra dimensions are curled, twisted, and folded. The universe becomes an instrument. Its properties, the laws of physics, emerge from how it is tuned. At these scales, space itself is not flat and empty. It's a canvas of microscopic geometry, tiny loops and folds at every point, too small to see. These structures define the allowed vibrations of strings, just as the shape of a violin defines its sound. This means that the fabric of the universe is not passive. It participates. It shapes what can exist. It selects which particles are allowed to arise, not by decree, but by the subtle contours of its hidden dimensions. In everyday life, we experience 3 spatial dimensions: up-down, left-right, forward-back. But in string theory, there are more, 10 dimensions in total, 9 of space, 1 of time, or 11, if you include certain extensions like M-theory. The extra dimensions are compactified, curled up so tightly that we cannot detect them directly, but their shape determines the physics we observe. This idea isn't just imagination, it's encoded in the mathematics, a specific shape for the hidden dimensions. A Calabi-Yau manifold, for example, will allow specific vibrational modes, and therefore specific particles. It's as if the geometry writes the symphony, and what we observe The particles, the forces, the constants of nature are simply the notes being played. One of the most striking implications of this is that matter and energy, diverse as they seem, might all come from the same fundamental source. The same kind of string vibrating in different ways. Just as white light splits into colors through a prism, so too can one type of string give rise to many kinds of particles. This helps explain something that puzzled physicists for decades: why the universe contains such a zoo of particles, each with their own properties, yet governed by a few simple forces. With string theory, the complexity arises from combinations and harmonics, not from a multitude of unrelated building blocks. Consider this: in particle physics, a property called spin is used to classify particles. Spin isn't literally spinning, it's a quantum property related to angular momentum. String vibrations produce spin naturally. Certain vibrational patterns correspond to spin-1 particles like photons, others to spin-1 particles like electrons. And in an elegant surprise, one particular vibrational mode gives rise to a spin-2 particle. This matches the properties of a hypothetical particle called the graviton, the quantum carrier of gravity. This is a major clue. Gravity emerges in string theory automatically. Unlike other quantum field theories where gravity doesn't fit neatly, string theory includes it from the start. The theory doesn't need to be modified to account for gravity. Gravity is built in, but this also introduces challenges. To preserve mathematical consistency, string theory requires conditions that don't match our classical intuitions. Supersymmetry is one of them. It's the idea that for every known particle, there's a superpartner, a mirror particle, with different spin characteristics. These superpartners haven't yet been observed in experiments, but they are a natural outcome of string theory's equations. In this framework, the world is not built from rigid building blocks, but from rhythmic pulses. Fields and particles emerge as the vibrations of strings, and their interactions arise from the ways those strings split, join, and collide. Imagine two strings colliding. They merge, form a loop, then break apart again. This process maps beautifully onto particle physics. Particles annihilating, creating new ones, exchanging force carriers. String theory visualizes these events not as points, but as smooth, continuous interactions. This also solves one of the most difficult problems in physics, the issue of infinities. When point particles interact, their equations often yield infinite results. Physicists patch over these problems using techniques like renormalization, but strings, being extended objects, avoid these issues. Their interactions are smeared out over a small region of space, eliminating the need for mathematical band-aids. This elegance is part of what draws so many to string theory. It replaces the chaotic zoo of particle physics with a unified, harmonious framework. Instead of dozens of particles, each with its own strange behavior, we get one principle: vibration. And from this principle emerges structure, not just electrons and quarks, but the very constants of nature. Why the electron has the mass it does, why the speed of light is what it is, why the universe has the laws we observe, all of it may be determined by the geometry of tiny curled dimensions and the vibrational patterns they allow. Of course, this raises profound questions. Why these vibrations? Why this particular geometry? Why this universe? Some physicists believe string theory doesn't point to just one universe, but a vast landscape of possibilities, a multiverse where different regions of existence play different symphonies. In one universe, gravity is stronger, in another, electrons are heavier, each shaped by different compactifications of the hidden dimensions, each its own song, echoing across a greater reality. This idea remains controversial, because if everything is possible somewhere, how do we test anything? How do we know which version is real, or whether they're all real? But from a mathematical perspective, the idea is compelling. The equations don't single out our universe as the only one. They allow a near-infinite range of variations, and the one we inhabit is simply the one whose song gave rise to stars, to chemistry, to life. So we return to the image: a string, vibrate, one tiny thread, invisible, delicate, elegant. Its ripples build the cosmos, its harmonics write the laws of physics, its structure gives rise to all things. Matter is music, fields are music, gravity, light, atoms, DNA, they are all melodies sung by the same hidden strings. And as we move deeper, we'll explore what happens when those strings interact, when they twist, merge, stretch, and fold, when they live on branes, surfaces within higher dimensional space, and how the fabric of the universe may be more than geometry. but a living, dynamic web of intertwined vibrations. The deeper we go, the more we find that physics is not just about things, but about patterns, about rhythm, about harmony, and maybe about beauty. The geometry of hidden dimensions. We live in a world with height, width, and depth. Three familiar dimensions navigated daily without thought. We move through them effortlessly, weaving paths through space. Time adds a fourth, flowing forward with relentless rhythm. These four dimensions form the fabric of our visible reality. But string theory tells us this fabric is incomplete. That beneath the surface, curled within every point of space, there lie dimensions we do not see. Extra directions hidden from our senses. Not because they don't exist, but because they are compact, wrapped tightly upon themselves like a scroll. These are not science fiction. They are required by the mathematics. Without them, string theory collapses. The equations demand additional dimensions to function, to cancel out infinities, to balance the terms, to keep the vibrations consistent and well-behaved. In most formulations, string theory needs 10 total dimensions, 9 of space, 1 of time. So where are the other 6? Why do we not perceive them? The answer lies in scale. The 3 large spatial dimensions, length, width, and height, are extended. They stretch vast distances from cities to stars. The other 6 are not stretched. They are curled, compactified, folded in upon themselves to such a tiny degree that even our finest instruments cannot detect them. Imagine an ant walking along a tightrope. From far away, the rope appears one-dimensional, just length. But the ant, being small, perceives 2 dimensions, the length of the rope and the circular dimension around its circumference. To a larger creature, that second dimension vanishes. It is still there, simply inaccessible. The extra dimensions in string theory work the same way. They are believed to be compactified on scales close to the Planck length, about 10 to the minus 35 meters, far smaller than any atom, far beyond the reach of our current tools. Yet, they may contain the most intricate geometry in the universe, because it is in their shape, their twistings and foldings, that the properties of strings are defined. In the early days of string theory, physicists searched for ways to describe these compact spaces, not just as abstract concepts, but as concrete mathematical structures. One class of shapes emerged as especially promising: Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xing-Tun Yau. These are 6-dimensional spaces with specific properties. They are compact, complex, and scalar, a type of symmetry condition. But most importantly, they allow supersymmetry to survive compactification. This makes them ideal candidates for describing the hidden dimensions of string theory. These manifolds are not like cubes or spheres. They are fantastically intricate. Imagine surfaces folded into themselves in multiple ways, with tunnels, holes, and warps in various directions. They are so rich in structure that no 2 Calabi-Yau shapes are exactly alike, just as no 2 snowflakes share the same form. And in their folds lie the rules of physics. The number of holes in a Calabi-Yau shape can determine the number of particle families. The arrangement of cycles repeating loops within the shape can dictate force strengths and coupling constants. Even the mass of particles may depend on how strings wrap around these tiny geometries. The geometry of the universe in this vision doesn't just sit there, it governs everything. From why there are electrons, to why gravity is weak. From why atoms hold together to why stars burn. All encoded not in code, but in shape. This is a radical shift in thinking. For centuries, physics sought simplicity, universal laws, constants, unchanging truths. But string theory, with its dependence on hidden geometry, suggests something deeper. That our physical reality emerges from the topology of tiny invisible dimensions. One implication is that different geometries could give rise to entirely different physics. If the Calabi-Yau shape were altered, the vibrational modes of strings would change. The particle spectrum would change. The universe would be different. This leads naturally to the concept of the landscape, a vast range of possible compactification geometries, each one potentially corresponding to a different universe with its own physical laws, particle types, and constants. Our universe in this view is one valley in a sprawling terrain of possibilities. But how do we choose which shape is real? What picks our particular Calabi-Yau manifold out of the many? No one knows for sure. Some physicists hope that deeper laws will emerge, selecting a unique solution. Others believe we are simply in a universe where the geometry happens to allow life, that we exist in this corner of the landscape, because only here could observers exist at all. This is the anthropic principle, controversial, but increasingly discussed in modern theoretical physics. It doesn't explain why the universe is the way it is, but it suggests why we might find ourselves in a particular version of it, not because it's special, but because it allows beings like us to ask the question. Regardless of interpretation, the mathematics of compactification is astonishing. It bridges fields from string theory to algebraic geometry, from topology to number theory. It connects physics with disciplines once thought purely abstract. The study of these extra dimensions has also produced unexpected insights. Dualities where one theory in a certain space is mathematically equivalent to another in a different space suggest that reality is not always what it seems. A compact space can mirror a large one. Two shapes can describe the same physics. The boundaries between geometry and field theory blur. This richness has led to cross-pollination between mathematics and physics, unseen since the days of Newton and Leibniz. Physicists use deep math to build physical models. Mathematicians find inspiration in physical theories. The two disciplines converge in pursuit of the hidden dimensions of the universe. And all of it, every string, every loop, every particle, depends on what cannot be seen. On spaces that hide beneath the surface of space. On dimensions that never stretch but always shape. On forms that curl inside the silence and give it structure. Even if we never see these dimensions directly, their effects ripple outward. They shape what particles exist. They determine how forces behave. They whisper the laws that atoms obey. This is geometry not as abstraction, but as destiny. A kind of hidden architecture, designing the scaffolding of nature, without ever revealing itself outright. It forces us to rethink what space is, not just emptiness, not just a backdrop, but an active player in physics, a sculptor, shaping what can and cannot exist. As we continue deeper into string theory, we'll explore the structures that live within these dimensions. Branes, membranes, and higher dimensional objects that stretch and move within the higher dimensional bulk. We'll examine how strings anchor to these surfaces and how those attachments shape the universe we experience. And we'll discover that these compact spaces may not just shape particles, but might hold the key to the origin of the cosmos itself. Branes, surfaces where strings live. Not all strings float freely through space. Some are anchored, some are tethered, bound not to points or particles, but to vast surfaces stretching through the higher dimensional cosmos. These surfaces are called branes, short for membranes, and they may be more than mathematical constructs. They may be the scaffolding of our reality itself. In the language of string theory, a brane is a multi-dimensional object on which open strings can attach their endpoints. Closed strings, like tiny loops, can drift freely, but open strings, those with two ends, need a place to terminate. That place is a brane. Branes come in many types. They are classified by their dimensions. The zero brane is a point, a one brane is a line, essentially a string. A two brane is a surface like a sheet, a three brane is a volume, and so on, climbing through higher dimensions. In some formulations of string theory, our entire universe may be a three brane, a three-dimensional surface floating in a higher dimensional space called the bulk. Everything we see, everything we touch, all matter and light, could be confined to this brane. And yet, just beyond our reach, higher dimensions stretch invisibly in all directions. This idea is more than speculation. It offers elegant solutions to long-standing puzzles. For example, why is gravity so weak compared to the other fundamental forces? The electromagnetic force holds atoms together. The strong force binds nuclei. But gravity? It's feeble. You can overcome its pull with a simple magnet. Brane world models suggest an explanation. Perhaps the other forces are confined to our three brane. But gravity, carried by closed strings, can leak into the bulk. It spreads into extra dimensions, diluting its strength in our slice of space. What seems weak here may be strong elsewhere, just spread too thin for us to notice. This changes our view of the universe. Instead of a singular three-dimensional space, we may live on a sheet, embedded in a vast, invisible superspace. Other branes may exist nearby, parallel universes, each with their own physics, their own matter and light, separated from us not by distance, but by dimension. And just as strings can vibrate, branes can ripple. They are dynamic, not static. They move, collide, fold and twist. Their motion affects the strings they anchor. The shape of a brane can influence particle properties, interaction strengths, even cosmological events. Some models suggest that the Big Bang itself was not a singular event from nothing, but the result of two branes colliding. In that moment, energy surged across dimensions, unleashing the fireball of creation. What we call the beginning may have been a crash between cosmic sheets, a higher dimensional event with lower dimensional consequences. This is called the ekpyrotic model, from the Greek word for conflagration. It offers a different perspective on cosmology, one where the universe didn't emerge from a point, but from the meeting of two extended objects, the bang not of expansion alone, but of interaction between branes. It also reframes our place in the cosmos. If branes can exist in parallel, what prevents others from floating close to ours? Could other universes lie just beyond a microscopic separation? Branes separated by a thin veil of bulk space, invisible, yet real. These ideas have captivated physicists, not just for their elegance, but for their explanatory power. They offer new ways to resolve puzzles about dark matter, dark energy, and cosmic inflation. Perhaps the strange behaviors we observe are not properties of our universe alone, but the result of influences from the bulk. Runners also provide a framework for understanding how dimensions behave. Why are 3 dimensions large and visible, while others are hidden? In some scenarios, only certain dimensions are compatible with the stability of branes and their interactions. The dimensions we observe may be the ones that support a stable brane world. The mathematics of branes extends into deep areas of geometry and field theory. The way strings attach, the tension of a brane, the way it curves through space, all influence the physical consequences. Branes can carry charges, they can warp space-time, they can form the basis of complex interactions between different regions of the universe. In string theory, branes are not optional, they are necessary ingredients. Without them, open strings cannot exist. And without open strings, we lose a vast range of physical phenomena: electrons, quarks, photons, the building blocks of matter. Branes also open the door to holography, the idea that a volume of space can be fully described by information on its boundary. This principle, born from black hole physics, gains new life in string theory. In some scenarios, a higher dimensional theory with gravity is equivalent to a lower dimensional theory without it, a strange but powerful duality that reshapes our understanding of what space even is. This is more than a mathematical curiosity. It implies that our universe might be a holographic projection from a higher dimensional reality, that the physics we observe is encoded on a distant boundary. Branes, in this view, become screens on which the cosmos is painted. And yet, they are not passive. Branes can evolve. They can expand, contract, fluctuate. They carry energy, exert force, and affect motion. In the early universe, branes may have played a central role in shaping evolution. They may still influence the structure of space-time today. In some models, black holes are described not as singularities, but as dense regions on branes, where strings become tightly packed. The boundary of a black hole may encode the information of everything it has swallowed, solving the information paradox through the language of strings and branes. This leads us to a deeper idea that space-time itself may be emergent, not fundamental, but a result of string and brane dynamics. If strings and branes are primary, and space-time arises from their relations, then what we call reality is not built from space, but from structure. That changes everything. It suggests that position, distance, and geometry are secondary concepts, emergent from deeper, more abstract rules. The ripples of strings, the vibrations on branes, the tension and curvature of these cosmic surfaces, these become the real ingredients. It also suggests that our universe is not isolated, that beyond the visible sky may lie entire regions of brane space, unreachable by light, but woven into the same overarching reality. The cosmos may be a collection of branes, each with its own laws, its own symmetries, its own songs. This is the essence of string theory's power. It doesn't just unify particles and forces, it unifies space and form, vibration and geometry, matter and structure. It replaces the idea of absolute location with dynamic interconnection. Branes are not just places, they are actors playing roles in the unfolding story of the universe. The dance of dualities. When theories mirror each other, in most sciences, two theories that look different are usually different. They give different predictions, follow different rules, and describe different things. But in string theory, something stranger happens. Two theories can look entirely different on the surface, different dimensions, different particles, even different shapes, yet secretly be the same, mathematically identical, physically equivalent, just two ways of describing one deeper truth. This idea is called duality. It is one of the most powerful and mysterious features of string theory, and it changes everything about how we understand the structure of reality. It suggests that what we perceive as fundamental may just be one version of a deeper, more flexible description. Reality may wear many masks, and duality is the thread that ties them all together. There are several kinds of duality in string theory. Each one reveals a different symmetry, a hidden connection, a bridge between what seem like entirely different landscapes. The first is T-duality. T stands for torus, a donut-shaped space. In string theory, when a spatial dimension is curled up into a circle like one of the hidden compact dimensions, T-duality says something strange happens. If the radius of the circle is very small, it behaves exactly like a circle of very large radius in a different version of the theory. Large and small become interchangeable. Space folds in on itself not just physically, but mathematically. Imagine walking around a tiny circular path. Small, you can barely move. Now imagine a much larger path, wide and open. T-duality tells us these two paths can describe the same physics, but only in the world of strings. Because strings can wrap around these circular dimensions, they can vibrate, or they can loop around, and the energy from wrapping behaves differently than the energy from vibrating. But when you switch the radius, small becomes large, large becomes small. The roles of those energies flip. The physics remains unchanged. This is not a metaphor, it is an exact equivalence. Two different shapes of space, two different versions of reality, yield the same physical outcomes when strings are involved. In a universe made of strings, the size of space becomes relative. Its meaning shifts depending on how you look at it. Another kind of duality is S-duality. Here, S stands for strong-weak. It suggests that a strongly interacting system in one theory can be mapped onto a weakly interacting system in another. This is astonishing. A problem that is impossibly complicated in one theory becomes simple in its dual. And vice versa. Imagine two physicists. One is studying a theory where particles are constantly colliding, interacting with overwhelming complexity. The other studies a quiet, gentle version of the universe, where interactions are rare and calculations are easy. Duality tells us they are studying the same thing. They just don't know it. Their equations are mirror images, reversed in strength but identical in meaning. Oh, this means the frontier of physics isn't always where we expect it. Sometimes, the hardest questions in one model are already answered in its dual, and in a deeper sense, this tells us that strong and weak forces are not opposites. They are two expressions of a unified structure. Then there is U-duality, which combines both T-duality and S-duality. It's the most comprehensive kind of symmetry, suggesting that entire families of string theories are linked together through these hidden connections. Like pieces of a puzzle, they slot together to form a single, coherent whole. For decades, physicists worked with 5 different versions of string theory. Each had its own rules, its own dimensions, its own quirks. They were called Type 1, Type 1AA, Type 1AA, heterotic SO, 32, and heterotic E8 bikes E8. At first, this seemed like a problem. Why should there be 5 theories of everything? But dualities changed the picture. They showed that these 5 were not competitors. They were aspects, reflections of a single underlying theory. Depending on how you look, what scale you probe, what assumptions you begin with, you reveal a different face of the same deep reality. This deeper structure was given a name, M theory. No one knows exactly what the M stands for. Some say it means membrane, others say mother, or mystery. What matters is that M theory is not just another version. It is the unifying story that contains all the others. In M theory, strings are just one kind of object. There are also membranes, 2-dimensional surfaces, and 3-dimensional branes, even higher dimensional objects called p-branes. The theory lives in 11 dimensions, not 10, and it suggests that the different string theories are just different limits, different viewpoints on this more complete framework. Dualities are what reveal this unity. They act like rotating a sculpture under light. From one angle you see a shadow that looks like type 1 string theory. From another, the shadow becomes type 1. Shift again, and you find heterotic E8 pikes E8. Each is real, each is partial. Only together do they reveal the full form. The existence of dualities changes the philosophy of physics. It suggests that our theories are not the final word. They are tools, maps of a terrain we have not yet fully seen. And just as one map may highlight rivers, another road's different theories emphasize different aspects of the same hidden structure. It also blurs the line between what's real and what's effective. In physics, we often distinguish between fundamental laws and effective theories that approximate them. Duality says that what's fundamental in one theory may be emergent in another. Reality, then, may not have a single hierarchy, but a network of equivalences. Even the concept of particles becomes relative. In one duality, a particle may appear as a soliton, a kind of stable ripple in another theory's field. In another, it may be a vibrating string or a wrapped brane. Identity is fluid, shaped by the language we choose. This flexibility extends to space and time. Some dualities relate theories in different numbers of dimensions. A theory in 3 spatial dimensions can have a dual in 2. This leads to the Ades CFT correspondence, one of the most celebrated dualities in modern physics. Ades CFT stands for anti-de Sitter conformal field theory. It links a gravitational theory in a curved spacetime with a quantum field theory on its boundary. In simple terms, it means that a world with gravity can be described entirely by a theory without gravity on a lower dimensional edge. It's like watching a movie projected on a screen. Everything happens on the screen, but the screen itself encodes a world with depth, mass, and motion. This isn't just a metaphor, it's a rigorous mathematical relationship. And it suggests that space-time and gravity may be holographic projections of more fundamental, non-gravitational laws. This holographic principle has reshaped how we think about black holes, entropy, quantum information, and even the origin of the universe. And it all stems from duality, from the idea that different descriptions can lead to the same truth. In the world of string theory, duality is not just a trick, it is a guiding principle. It tells us that no theory is isolated, that each version, no matter how complete it seems, is just a facet of something more vast. It also offers a kind of humility. What we call a breakthrough today may tomorrow be revealed as just one corner of a mirrored hall, a fragment of a deeper whole. And yet, this isn't cause for despair, it's cause for wonder, because in duality we find unity, not a single answer, but a web of truths, each reflecting the others in a grand cosmic dance. Supersymmetry in the shadow world of particles. Beneath every known particle, beneath every field and force, there may lie a hidden mirror, a shadow counterpart, a silent partner. Supersymmetry suggests that the world as we know it is only half the story. Supersymmetry, often abbreviated as SUSY, is an extension of quantum field theory. It proposes that for every fundamental particle we've discovered, there exists a superpartner. These partners are not just duplicates. They differ in a specific and crucial way. Spin, in quantum physics, is not literal spinning. It is a kind of intrinsic angular momentum, a fundamental property that classifies particles. Fermions, like electrons and quarks, have half-integer spin. They make up matter. Bosons, like photons and gluons, have integer spin. They carry forces. Supersymmetry links these two realms. For every fermion, there exists a bosonic superpartner, and for every boson, a fermionic one. Electrons gain selectrons, quarks gain squarks, photons gain photinos, glucils gain glucilses. These superpartners are not just theoretical curiosities. They could solve some of the biggest puzzles in physics. Why is the Higgs boson so light, despite quantum corrections that should make it enormously massive? Why do the strengths of the fundamental forces almost, but not quite, unify at high energies? Supersymmetry offers answers. It tames the mathematical infinities that plague the Higgs mechanism. It smooths out the running of coupling constants, those numbers that determine how strong each force is, allowing them to converge in a way that hints at grand unification. But SUSY doesn't just help with equations, it fits beautifully into string theory. In fact, String theory needs it. Without supersymmetry, the mathematics of strings becomes unstable, inconsistent. Certain anomalies appear, frequencies clash, the elegant harmony collapses. Supersymmetry stabilizes the vibrations, it balances the equations. In a supersymmetric string theory, the modes of vibration for bosons and fermions cancel out unwanted infinities. The theory becomes whole. This leads to superstring theory, the version of string theory that includes supersymmetry. It's not optional, it's embedded, and it extends the unification even further, not just of forces and particles, but of statistics and spin, matter and motion. And yet, we haven't seen any superpartners. Despite decades of searching, not one has been observed. Particle colliders like the Large Hadron Collider have smashed protons together at enormous energies. They found the Higgs boson, but no sign of squarks, gluinos, or neutralinos. So where are they? If supersymmetry is real, why haven't we detected its shadow world? One answer is that supersymmetry is broken. Not destroyed, but hidden. In its perfect form, superpartners would have the same mass as their visible twins. But in our universe, that symmetry may be spontaneously broken, just as a pencil standing on its tip eventually falls. When SUSY breaks, the superpartners gain mass. They become heavier than their counterparts. Too heavy perhaps for current colliders to detect, still out there, still real, just out of reach. And yet, they may leave fingerprints. One of the most intriguing possibilities is that the lightest supersymmetric particle, often called the LSP, could be stable, unable to decay into anything else. And if that's true, then it might still be here, floating through space, streaming through galaxies, passing through you, even now, invisible, silent, massive. A candidate for dark matter. Dark matter is one of the great mysteries of modern astronomy. We can't see it, but we see what it does. It holds galaxies together. It bends light from distant stars. It outweighs visible matter by a factor of 5, and yet it has never been directly observed. Supersymmetry offers a possible answer. The LSP, perhaps a neutralino or gravitino, could be the invisible mass that fills the cosmos. Stable, weakly interacting and abundant. Not just a theoretical echo, but a real and fundamental part of our universe. This connects the smallest and the largest scales. The physics of vibrating strings, governed by quantum mechanics and supersymmetry, may determine the fate of galaxies and cosmic structure. A theory born in equations might explain the architecture of the heavens. Supersymmetry also provides tools for exploring the early universe. In the fractions of a second after the Big Bang, temperatures and energies were high enough for SUSY particles to roam freely. Their properties could have influenced inflation, baryogenesis, and the eventual formation of matter as we know it. And while we may not yet see these particles directly, string theory's inclusion of supersymmetry gives it a kind of completeness. It weaves together particles and forces into a single, balanced framework. Every particle has a role, every vibration has a mirror, every dance has a partner. But this mirror world isn't just a tidy addition, it transforms the entire landscape. It changes how we write the equations. It changes how we understand symmetry itself. Because supersymmetry isn't a reflection. It's an operation, a transformation that turns fermions into bosons and back again. It's a generator, a way of moving through the space of fields. And in this sense, it's more than a convenience. It's a fundamental principle, perhaps as deep as relativity or quantum mechanics. Some have even speculated that supersymmetry is the key to space-time itself, that without it, the geometry of the universe would fall apart, that strings could not vibrate, branes could not stretch, and dimensions would not hold together. And yet, supersymmetry remains in limbo, elegant, necessary, beautiful, but unconfirmed. We await evidence in particle accelerators, in cosmic background radiation, in the deep silence of underground dark matter detectors. Perhaps the signs are there, whispering just beneath the noise. String interactions and the quantum fabric of space. If everything is made of strings, then reality itself must be woven. Not in a metaphorical sense, but quite literally stitched together by loops, threads and oscillations at the smallest conceivable scale. In classical physics, particles are points. They have no size, no internal structure. They move through space, collide and bounce like billiard balls. An elegant model, but one that falters at quantum scales. Point particles, when treated mathematically, often lead to infinities. Their interactions become violent, unstable. The closer you zoom in, the worse the equations behave. String theory changes the game. Particles are not points, but tiny loops of vibrating energy. They are not fixed in form, but dynamic, always in motion, always in resonance. And when these strings interact, they do not collide at a single point. They merge, split, and reconnect in smooth, continuous ways. This smoothness is crucial. When two strings meet, they do not explode into singularities. They blend. Imagine two soap bubbles brushing into one another, joining into one, then splitting again into new combinations. The interaction is not violent. It is fluid, and the mathematics reflects this fluidity. There are no infinite spikes, no mathematical chaos, only soft transitions from one state to another. These interactions are what give rise to all forces. When two particles interact, what's really happening is that two strings are joining and exchanging energy. The electromagnetic force. A photon string mediates it. The strong force, gluon strings exchanged between quarks. Even gravity, the elusive, stubborn force, arises from the exchange of graviton strings. And these graviton strings, unlike photons, can propagate freely into the bulk. They are closed loops, unchained from branes, capable of moving through the higher dimensional space. This may explain why gravity appears so weak. It spreads its influence across more dimensions than the other forces can reach. But these string interactions are not just about forces, they are about structure. They define how particles behave, how they evolve, how they scatter and recombine. And they hint at something deeper, that space itself may not be a backdrop for strings, but a consequence of them. This idea is radical. It suggests that space-time is not a pre-existing arena. Instead, it emerges from the quantum interactions of strings, that the distances we measure, the time we perceive, the geometry we live within, are all byproducts of vibrational behavior at the smallest scale. At this scale, there is no clear distinction between space and matter. A loop of string is both a particle and a ripple in geometry. Its motion defines position. Its frequency defines time. Its tension defines curvature. It is the universe in miniature. And when many strings interact, they form a network, a kind of quantum foam. This foam, unimaginably small and chaotic, may be the true foundation of space-time. Instead of a smooth, continuous fabric, we find a frothy structure, constantly shifting, constantly rearranging itself. This quantum foam is not directly visible. It lies below the Planck scale, beneath the reach of microscopes and colliders. But its effects may ripple outward. They may influence the vacuum energy of space. They may play a role in black hole entropy. They may hold the key to reconciling quantum mechanics with gravity. One way physicists explore these interactions is through something called the string worldsheet. Instead of tracking a particle's path through time, we track the surface traced out by a string as it moves. This surface, like a soap film drifting in the wind, is governed by complex equations. Its curvature, its tension, its boundary conditions all contribute to the behavior of the string. The worldsheet is where the physics happens. It's where string interactions are calculated. It's where forces are exchanged, where vibrations meet and merge. And it is inherently quantum, fluctuating, probabilistic, described not by certainties, but by amplitudes and superpositions. This probabilistic nature is what allows strings to do more than just move. They can interfere with themselves, cancelling out or amplifying certain outcomes. They can exist in multiple states at once, a superposition of notes, a harmony of possibilities, and the sum of all possible paths, all possible shapes of the worldsheet is what determines the result of any given interaction. This is the path integral approach, borrowed from quantum field theory, but extended into a richer, more geometrical language. What emerges from this complexity is a vision of the universe, not as a machine of parts, but as a web of patterns, a symphony, not of sound, but of geometry. Every interaction, every force, every particle is a motif in this music. Each vibration is a note, each joining of strings, a change in melody, and space, far from being a container, is the music itself. Even the topology of space may be affected by string interactions. In classical physics, the shape of space is fixed. But in string theory, it can change. A process called a topology change allows strings to tunnel between different configurations, transforming one kind of space into another. This opens doors to ideas previously thought impossible. Universes that evolve, not just in size, but in shape. Dimensions that rearrange, space that folds, reconnects, even tears, only to heal itself through the dynamics of strings. These transitions aren't just mathematical games, they could happen in the early universe. They might shape the birth of galaxies, the expansion of space, the very nature of cosmic inflation, and they might leave behind relics, subtle imprints in the cosmic microwave background, or signatures in the gravitational waves rippling through the void. But to trace them, we must understand string interactions not just as equations, but as events, as histories written in geometry, as stories told by vibrating lines and rippling surfaces. At this level, cause and effect blur. A single interaction may involve countless histories overlapping, interfering, coalescing into one observed outcome. And yet, through all the complexity, a pattern emerges, a balance, a consistency, strings that interact according to simple, universal principles, worlds that evolve from shared mathematical foundations. Compactification, curling up the hidden dimensions. Roughly 5 billion years have passed since the Big Bang. The universe, once filled with a near-uniform plasma, has evolved into a structured web of galaxies, stars, and increasingly complex chemistry. The period of rapid star formation is beginning to decline, and while the universe is still active and luminous, its transformation has entered a new phase, one defined not just by birth but by organization. The cosmic web continues to grow in complexity. Galaxies trace the filaments shaped by dark matter, forming clusters at intersections and vast empty voids between these filaments, composed of galaxies and gas, span hundreds of millions of light-years. Their patterns reflect the large-scale gravitational influence of both ordinary and dark matter, shaped by initial conditions seeded in the earliest moments of cosmic history. Within this web, gravitational collapse becomes the dominant process driving structure. Gas accretes onto galaxies through cold flows along the filaments. These flows fuel central star formation, while interactions and mergers stir galactic evolution. The gas itself is subject to shocks, heating, and feedback from star formation and active galactic nuclei. But all of this visible structure is only part of the story. For those studying the deeper architecture of the universe, those who dare to ask how the laws of physics arise in the first place, another kind of structure becomes relevant, one not visible in telescope images, not mapped by redshift surveys, but encoded in the tiniest folds of space itself. It is the shape of the hidden dimensions, the extra 6 or 7 spatial dimensions required by string theory beyond the familiar 3, do not extend across the cosmos in the way we experience length, width, and depth. They are curled up, compactified into minuscule geometries so small that they have eluded every experimental probe. This compactification is not an afterthought, it is essential. Without it, string theory would describe a universe with far more dimensions than we see, and yet, the way those extra dimensions are compactified determines everything about the physics we do see. The process is like folding a vast origami from an infinite sheet. The final shape depends on how you crease it, how you twist each section, how each fold interacts with the rest. In string theory, this origami is 6-dimensional, and it folds into a shape known as a Calabi-Yau manifold. These are not ordinary geometric objects. They are exquisitely complex, smooth, compact spaces with specific curvature properties. Their topology includes holes and cycles of various dimensions, and each of these cycles can be wrapped by strings or branes, producing unique physical effects. The number of holes in a Calabi-Yau shape, for example, helps determine the number of particle generations in our universe. We observe 3 electrons, muons, and taux, along with their corresponding quarks. In the mathematics of compactification, this triplet emerges naturally from the topological data of the curled-up space. Even the values of fundamental constants like the strength of electromimetic interactions or the masses of particles can be traced back to the shape of these dimensions. Change the geometry, and the physics changes, alter the number of folds, and you might live in a universe with no atoms, no stars, no chemistry. This leads to a stunning realization. What we perceive as immutable laws of physics may in fact be local environmental conditions. They are not dictated from above, but emerge from the particular geometry of our hidden dimensions. We do not merely inhabit the universe, we inhabit a particular solution to the equations of string theory, a particular folded space. There are many ways to compactify dimensions, and each method creates a different kind of low-energy physics. This gives rise to the so-called string landscape, a vast collection of possible vacua, each corresponding to a different compactification scheme. Estimates suggest there may be on the order of 10,500 different possible compactifications. That's a 1 followed by 500 zeros, more than the number of atoms in the observable universe. Each one a different version of reality, each one a different set of laws, forces, and particles. Our universe is just one point in this vast multiverse of possibilities. Some physicists view this as a problem. If anything is possible, what can we predict? What becomes of testability, of falsifiability? But others see it differently. They argue that this landscape offers an explanation for the peculiar fine-tuning of our own universe. Why do the constants of nature appear so delicately balanced for life? Why do small changes in fundamental parameters lead to a dead, lifeless cosmos? In a single universe theory, these coincidences seem miraculous. But in a landscape of compactifications, it is expected. We find ourselves in a universe that permits life, because only such universes can contain observers. This is the anthropic principle, controversial, but increasingly considered, not because it answers why, but because it explains why here, among a sea of possible worlds, we naturally find ourselves in one where questions can be asked. Compactification doesn't just affect constants, it affects symmetries. Certain geometries preserve supersymmetry, while others break it. Some allow chiral fermions, a key ingredient in the standard model. Others do not. This connection between geometry and particle physics has deepened over the decades. Physicists and mathematicians now work together to classify possible compact spaces, catalog their features, and understand how they map to the physics we observe. The modulo space of compactifications, a kind of parameter space describing the shapes of extra dimensions, is vast and rich. Some regions correspond to stable universes, others to unstable or transient ones. Transitions between regions may be possible through quantum tunneling, implying that even the shape of the universe could evolve over time. At a deeper level, compactification challenges our intuition about dimensionality itself. We think of dimensions as fixed, as a basic feature of reality. But in string theory, they are emergent. They arise from deeper principles, and how they are compactified is as important as whether they exist. Imagine a universe where only 2 spatial dimensions are large, or where 7 are visible and 3 are curled. The physical laws would be different. Atoms might not form. Forces would behave unpredictably. The very notion of locality, what is near and far, would be transformed. Compactification also links to the idea of flux. In many models, fields can wrap around cycles in the compact dimensions. These fluxes stabilize the shape, much like pressure holds up a balloon. They prevent the curled space from collapsing or expanding, anchoring the geometry in a stable configuration. These fluxes add richness to the landscape. They allow many more solutions, each with its own internal logic, and they provide a mechanism for selecting among the vast array of possibilities. But we do not yet know which compactification is ours. We search for clues in the values of constants, in the behavior of particles, in the echoes of the early universe. Perhaps someday, we will decode the precise geometry of our hidden dimensions. Until then, we continue this, not just outward, into space, but inward, into the folds beneath perception, where space itself is curled into the shape of reality. Time flows, at least that's how we feel it. Moments slip away like water through fingers. One instant replaces the next, and with it change unfolds. But what is time, really? Is it a backdrop against which events occur? Or is it something woven into the very fabric of the universe? In everyday life, time feels absolute. It marches forward, unbending and universal. But in physics, time is slippery. Einstein showed us that it can bend, stretch, and twist. That it flows differently depending on your speed and position. 2 observers in relative motion do not agree on what now means. Time, it seems, is not a single river, but a collection of branching streams dependent on perspective. String theory inherits this complexity, but it adds something more. It suggests that time, like space, may not be fundamental. That the passage of time, the ticking of every clock, could be an emergent feature of deeper, more subtle structures. In classical mechanics, time is a parameter. It orders events. In quantum mechanics, it becomes a puzzle. The Schrödinger equation, which governs how systems evolve, requires time as an external input. But in general relativity, time is part of the geometry. It bends with gravity, it warps near massive objects, and near a black hole, it almost stops. These two views of time, external versus geometric, clash. Quantum mechanics wants a fixed timeline. Relativity wants a flexible one. String theory attempts to reconcile both, and in doing so it raises a new possibility that time itself might be derived from the behavior of strings. Strings vibrate, and vibration implies rhythm, oscillation, the kind of ticking, but the ticking of a string is not measured against a background clock. It is intrinsic. The string measures time for itself. In this way, time becomes relational, not something that exists on its own, but something that emerges from the relationships between systems, a network of vibrations, each influencing the other. Time is what happens when one thing changes relative to another. This mirrors an ancient idea that time is not a substance, but a measure of motion. Aristotle said that time is the number of change with respect to the before and after. In string theory, that philosophy takes on a new mathematical life. Some physicists speculate that in the deepest formulation of string theory, there is no time variable at all, no global t to measure progress. Instead, there is only the configuration space of strings, their shapes, their connections, their interactions, and what we call time is an attitude we assign to describe how one configuration morphs into another. This idea is clearest in the Wheeler-DeWitt equation, a foundational equation in quantum gravity. It lacks a time parameter. It describes a universe where the whole configuration exists all at once. No past, no future, just a timeless state. Evolution arises only when we pick one variable to play the role of a clock and watch how others change with respect to it. In string theory, the equivalent idea can be found in the worldsheet formalism. Instead of a timeline, you have a two-dimensional surface, one dimension for the string's length, one for its evolution. This evolution doesn't need an external time, it's built into the geometry of the worldsheet itself. Time in this view is not something we observe, it is something we define. We select a measure of change and call it time, but the universe itself may not care, it simply exists, with all its configurations written in the language of strings. This leads to radical possibilities. Could the flow of time be an illusion? Could the directionality of time, the so-called arrow of time, be a byproduct of entropy or of initial conditions? In thermodynamics, the arrow of time points from order to disorder, from low entropy to high. The past is more organized than the future, but the laws of physics themselves are time symmetric. They do not prefer forward or backward. They allow both. String theory, being built on these laws, shares this symmetry. It does not tell us which direction time should move. It only describes interactions that are reversible in principle. So why do we remember the past, but not the future? One answer may lie in cosmology. At the Big Bang, the universe began in a state of extremely low entropy. Highly ordered, this initial condition set the direction of time. And as the universe expands, entropy increases. Structure dissolves. Stars die. Complexity gives way to thermal noise. In this sense, time's arrow may be tied to the universe's shape, and thus to the compactification of dimensions, the geometry of branes, and the topology of the cosmic landscape. In some models, entire regions of the universe may evolve with time flowing in different directions, or looped time structures could exist within certain string configurations. Time may not be a single thread, but a braided strand with multiple directions and pathways. The study of closed time-like curves explores these possibilities. They are loops in space-time that return to their origin, allowing for what might be interpreted as time travel. Though still speculative, string theory's flexible space-time geometries make such constructs more plausible, at least mathematically. There are also models of timeless cosmology. In these, the universe is described not by how it evolves, but by how all configurations coexist. Observers perceive change because they experience one slice of this whole. The passage of time becomes a trick of consciousness, a filtering of a timeless structure. Yet, for us, time feels real. We age, we remember, We anticipate our experience of time is among the most intimate features of being. String theory, while abstract, does not deny this. Instead, it asks, what causes this experience? How does a universe built from timeless equations give rise to the sensation of now? One possibility involves decoherence. Quantum systems can exist in superpositions, but interaction with the environment forces them into definite outcomes. This process defines a direction. The collapse of possibilities into actuality creates the illusion of flow. Another angle comes from holography. In the Adshila CFT correspondence, the boundary theory is timeless. It exists as a whole, but the bulk theory, where gravity lives, includes time as a geometric dimension. This suggests that time may emerge when a non-gravitational system is projected into a gravitational one. If true, then our experience of time might be a projection, a side effect of living in a universe with gravity. Time could be an emergent direction, not a fundamental axis. This reshapes how we think about causality, prediction, and memory. It forces us to reconsider what it means for something to begin or end, and it opens the door to a more fluid conception of reality. In a universe made of strings, perhaps time is a song, not a line, but a rhythm. Not a ticking clock, but a melody woven from vibration and form. Black holes and the string theory paradox. At the edge of known physics lies a shadow, a place where gravity becomes extreme, where time slows to a crawl, and the fabric of space folds inward. This is the black hole, a region so dense, so curved, that not even light can escape. Black holes are no longer mysterious monsters. They are now known to be common, lurking at the centers of galaxies, wandering through space, and forming from the depths of massive stars. Yet despite our growing observational power, they remain theoretical battlegrounds, places where general relativity and quantum mechanics refuse to cooperate. The trouble begins with information. In classical physics, a black hole is defined by three simple parameters: mass, charge, and angular momentum. Everything else, the material that formed it, the structure of atoms, the chaos of collapse, disappears behind the event horizon, lost to the whirl. This is fine in classical physics, but in quantum mechanics, information cannot be destroyed. The evolution of quantum systems is unitary, which means the past must always be recoverable from the present. This leads to a paradox. If a black hole forms and then evaporates through Hawking radiation, what happens to the information? Stephen Hawking proposed in the 1970s that black holes do emit radiation, a faint glow caused by quantum fluctuations near the event horizon. This Hawking radiation carries energy away, causing the black hole to shrink. Eventually, it may vanish completely. But the radiation is random, it contains no trace of the matter that fell in. And if the black hole disappears, then so too does the information it once contained. This violates quantum mechanics. It suggests that the laws of physics are inconsistent. This is the black hole information paradox, one of the deepest puzzles in all of theoretical physics. And string theory, with its extended objects and rich mathematical structure, offers a path toward resolution. The key insight comes from string theory's treatment of black hole microstates. In standard general relativity, a black hole is smooth and featureless, but in string theory, you can build a black hole out of strings and branes. Different combinations of wrapped branes and vibrating strings can produce the same macroscopic properties: mass, charge, spin. But each configuration is different. Each one corresponds to a different quantum microstate. And when you count these configurations, you get a number, the logarithm of which matches the entropy of the black hole. This is no coincidence. In thermodynamics, entropy is a measure of the number of internal states. In the 1970s, Jacob Bekenstein and Stephen Hawking derived a formula for black hole entropy based on the area of the event horizon. It was mysterious. Why should area, not volume, determine entropy? String theory gives the answer. It shows that the number of microscopic string brane configurations corresponds exactly to the entropy derived from area. The horizon area is not just geometry, it is a reflection of invisible complexity. This was one of string theory's great triumphs. It suggested that black holes are not information sinks. They are structured, they have internal states, and the Hawking radiation, far from being random, may be shaped by these states. But how can information escape? If the event horizon hides all structure, how does the radiation carry it out? One proposal involves black hole complementarity. This idea suggests that information is both inside and outside the horizon. depending on your point of view. To an outside observer, the information is encoded in the radiation. To a falling observer, it remains inside. No contradiction arises, because no observer can access both descriptions at once. Another bold idea is the fuzzball proposal. It argues that black holes, rather than having a smooth horizon, are made entirely of strings and branes in highly tangled configurations. There is no true interior, just a complex, stringy surface. The radiation comes from this surface, which retains memory of the initial state. This resolves the paradox by eliminating the horizon. No interior means no place for information to hide. Everything is on the outside. And the complexity of the fuzzball allows for subtle patterns in the radiation to carry information back out into space. These ideas remain speculative, but they offer hope. They suggest that string theory can unite quantum mechanics and gravity in a way that respects both. It also offers new tools for understanding black hole dynamics through the AD-CFT correspondence. A black hole in a curved gravitational spacetime is dual to a thermal state in a quantum field theory on the boundary of that space. This means you can study black hole evaporation by looking at quantum entanglement in a lower dimensional system. You can calculate the flow of information, the growth of entropy, and the recovery of quantum data using ordinary quantum mechanics. This is profound. It suggests that black holes are not special exceptions. They are quantum systems like any other. Their mysteries arise not from paradox, but from our limited understanding of quantum gravity. String theory also suggests that black holes may not destroy spacetime, but weave it. Their dynamics influence the geometry around them. Their evaporation may leave behind a changed topology, a ripple in the quantum foam. And perhaps at the end of their lives, they do not vanish, but transition into new objects, Planck-scale remnants, or bursts of strings, or tunnels to other regions of space. The true fate of black holes remains unknown. But string theory gives us tools, not just for speculation but for calculation. It replaces paradox with possibility, ignorance with inquiry. And in doing so, it reimagines the black hole, not as a dead end, but as a laboratory, a place where the deepest ideas of physics converge, where vibration and curvature collide, and where the answers to the biggest questions may one day emerge. The holographic principle and the illusion of space. We think of space as volume, length, width, and depth. We imagine the universe as vast and three-dimensional, stretching in every direction. But what if this depth is an illusion? What if the contents of our universe, stars, planets, particles, and even time, are all encoded on a distant surface? What if reality is, in a very literal sense, a hologram? This is the idea behind the holographic principle. It's not science fiction. It is a serious proposal, grounded in black hole physics and string theory. It suggests that all the information contained within a volume of space can be described by a theory on the boundary of that volume. That the three-dimensional world we move through is emergent, a projection from something two-dimensional. To understand how this works, we begin with black holes. Decades ago, physicists discovered something peculiar. The entropy of a black hole is not proportional to its volume, but to the area of its event horizon. This is counterintuitive. Entropy typically scales with volume, more space, more information. But black holes break that rule. Their entropy, the number of microscopic states they can have, scales with surface area. This led to a realization: if the entropy of a black hole is determined by its surface, then maybe the information about everything it contains is also encoded on that surface. And if black holes follow this rule, perhaps the universe does too. This radical idea was first proposed by Gerard Hooft and developed further by Leonard Susskind. They suggested that our three-dimensional world could be described by a quantum field theory on a distant two-dimensional boundary. This is not just metaphor, it is mathematics, and string theory provides the framework to make it precise. The most famous realization of the holographic principle is the AD-CFT correspondence, discovered by Juan Maldacena in 1997. It describes a duality between two very different theories. On one side, a gravitational theory in a curved five-dimensional spacetime called anti-de Sitter space, ADS. On the other, a conformal field theory, CFT, living on the four-dimensional boundary of that space. These two theories are not approximations, they are equivalent. Every object, every interaction, Every quantum fluctuation in the gravitational theory has a counterpart in the boundary theory. Space-time geometry over here maps to quantum entanglement over there. This is the essence of holography. A bulk theory, with gravity, is dual to a boundary theory. Without it, you can study one to learn about the other, and the deepest features of space, distance, curvature, topology, can be reinterpreted as patterns of information on the edge. The implications are staggering. It means that gravity might not be fundamental. It may be a byproduct of the way quantum information arranges itself. The fabric of space might emerge from entanglement, not as a stage on which physics plays out, but as a consequence of deeper informational rules. In this view, distance is not a measure of location. It is a measure of how entangled two systems are. The closer two regions are in space, the more entangled they are in the boundary theory. As entanglement changes, so too does the geometry of space. This reimagines space-time as a code, a kind of quantum error-correcting code, capable of maintaining coherence, protecting information, and recovering structure from subtle distortions. In recent years, physicists have mapped black hole interiors to complex patterns of entanglement in the boundary theory. They've modeled wormholes, time evolution, even teleportation protocols, all using purely quantum systems with no gravity at all. This leads to a stunning conclusion: space and time may be emergent, not just in some philosophical sense, but in a calculable, testable way. What we call the inside of a region is defined by how information behaves on its boundary. And if our own universe follows similar principles, even if we do not live in an anti-de Sitter space, then perhaps our three-dimensional cosmos is just the shadow of something deeper. In some models, our entire universe might be a kind of boundary theory of a higher dimensional space that we never directly observe. We are not inside the bulk, we are the bulk. Of course, we don't see a projection, we see a world. We experience distance, motion, gravity. The holographic principle doesn't deny this. It explains it. It tells us that our experience is real, but that its source may lie in a more fundamental theory. This has profound consequences. It reframes the laws of physics as a kind of compression, a boundary system containing the full story of everything inside. And it provides a new language for talking about black holes, cosmology, and the nature of quantum gravity. Because if everything is encoded on the surface, then perhaps nothing is truly lost. Information is preserved not inside, but on the edge. This might be the resolution to the information paradox. Hawking's radiation isn't random. It is the result of a unitary process happening in the dual theory. The black hole evaporates, but the boundary retains the script. Even time may be part of this encoding. Moments unfold in the bulk, but correspond to static configurations in the boundary system. What we call evolution is the reading of a holographic script. String theory provides the machinery to make this more than philosophy. It gives us a way to map geometries to entanglement, to calculate curvature from entropy, to build space from scratch. We still don't know whether our universe obeys a precise holographic duality, but every hint, every successful model, suggests that space-time is not what it seems. It is not a substance, it is a story, told in the language of fields, entanglement, and vibration, written not across vast distances, but on the faint outlines of the cosmic boundary, the landscape, a multiverse of possible realities. In every fundamental theory of physics there lies a question too large to ignore. Why these laws? Why these constants, these particles, these forces? Why not others? Why is the electron's mass what it is? The strength of the strong force so precisely tuned, or the cosmological constant so extraordinarily small? Centuries physicists sought a unique answer, a single elegant theory that would explain why the universe is exactly this way and no other, a theory of everything, whose structure would determine the values of all observable parameters from first principles. But string theory, despite its elegance and power, does not offer just one solution. It offers many, an almost unfathomable number of them. Each solution corresponds to a different way of compactifying the extra dimensions, a different configuration of fluxes, a different vacuum state. This vast collection of solutions is known as the string landscape. It is not a metaphor, it is a real, calculable structure within the theory, defined by the many possible choices for the geometry and topology of the compactified dimensions, the values of various fields, and the presence or absence of extended objects like branes. Each point in this landscape corresponds to a different universe, a different set of low-energy physical laws, a different spectrum of particles, a different cosmological constant, and, critically, a different potential for complexity. The number of these solutions is enormous. Early estimates, based on configurations of flux compactifications in type IB string theory with Calabi-Yau orientifolds, suggest a number on the order of 10^500. That's 1 followed by 500 zeros. Each solution represents a metastable vacuum with its own self-consistent internal physics. In most of these vacua, the physics would look nothing like ours. Some would have no stable matter. Others might have radically different nuclear chemistry. Many would lack the conditions necessary for galaxies, stars, or any form of life, but a small subset, perhaps vanishingly small, would have properties similar to our own. This leads to a new way of thinking about physical law. Rather than being uniquely determined, the laws we observe may be selected from a much larger ensemble based on anthropic criteria, not because the universe is fine-tuned for us, but because we can only exist in those regions where the conditions permit complex structures to arise. This is the anthropic principle in its most pragmatic form. In a multiverse governed by string theory, observers naturally find themselves in regions of the landscape where conditions allow them to exist. It is not a mystical statement, it is a statistical one. The most pressing example of this is the cosmological constant problem, vacuum energy. The energy density of empty space is observed to be Nizai, but incredibly small, roughly 10^120 in Planck units. If it were even slightly larger, the accelerated expansion of space would have prevented galaxies from forming. From a traditional perspective, this seems absurd. Why would nature choose such a small number? But in the landscape picture, the cosmological constant is not chosen once and for all. It is a random variable, taking different values in different vacua. Most vacua have large values. Only a small subset have values small enough to allow the formation of cosmic structure. Our universe is simply one of those rare regions, and because observers can only exist in such regions, the smallness of the cosmological constant is not a surprise. It is a selection effect. This line of reasoning was made concrete in the early 2000s by the work of Raphael Brousseau and Joseph Polchinski. They showed that with sufficient numbers of fluxes, quantized field strength, wrapping cycles in the compact dimensions, a densely spaced set of possible vacuum energies arises. These fluxes are discrete, they cannot be continuously adjusted, but with enough of them, the landscape becomes densely populated. This makes it statistically likely that some vacua will have properties like ours. Later, the KKLT construction, named after Kac-Crew, Kalosh, Linde, and Trivedi, showed how to stabilize moduli fields in such flux compactifications. Moduli are scalar fields that describe the shape and size of the compacted dimensions. If they are unstabilized, they lead to unphysical behavior, massless scalars, unbounded potential energy. The KKLT mechanism showed how fluxes and non-perturbative effects could lock these moduli into place, producing metastable de Sitter vacua regions of space with positive vacuum energy that expand exponentially like our own observed universe. These metastable states are not forever. They may eventually decay through quantum tunneling to lower energy vacua. This decay process is described by Coleman-de Lucha instant solutions to the Euclideanized field equations that describe bubble nucleation. When such a bubble forms, it expands at nearly the speed of light, converting the parent vacuum into a new region with different physical laws. If our universe is a metastable vacuum, then someday, perhaps billions of years from now, it may decay in this way, wiping out everything within it. This sounds terrifying, but it also connects our universe to a broader cosmological framework called eternal inflation. In these models, inflation never ends everywhere. While inflation ends in some regions like our observable universe, it continues indefinitely elsewhere, producing new pocket universes with each decay. Each pocket corresponds to a different point in the string landscape. Each has its own physical constants, its own vacuum energy, its own dimensional compactification. The multiverse is not a theoretical indulgence, it is the natural cosmological interpretation of the string landscape. Of course, the landscape presents challenges. It complicates the goal of unique prediction. If any set of constants can occur somewhere, what does it mean to explain them? How do we distinguish prediction from postdiction? Some argue that we must embrace a new style of reasoning, statistical and anthropic. Others seek deeper selection principles, perhaps rooted in cosmological dynamics, quantum gravity constraints, or entropy bounds. There is also the question of measure. In an infinite multiverse, how do you assign probabilities to outcomes? What does it mean to say that a universe is typical or rare? Different regularization schemes yield different conclusions. This is known as the measure problem, and it remains unsolved. Yet despite these challenges, the landscape has become a central feature of string theory research. It has shifted the questions we ask, and reframed how we think about fundamental physics. Instead of seeking a single unique answer, we seek the statistical structure of possibilities. And that is a revolution in itself, because it means our universe may not be the only universe, nor the necessary one. It is one of many, a drop in a sea of configurations, selected not by logic, but by existence. String theory stood not as a single theory, but as 5 distinct frameworks, each consistent in its own domain, each describing vibrating strings in 10-dimensional spacetime, each with its own symmetries, dualities and brane structures. These were the Type 1, Type 1IA, Type 1IB, heterotic SO32, and heterotic E8 by E8 string theories, and for a time, it seemed that this multiplicity was a flaw, a complication to be resolved, a sign that something was still missing. But in the mid-1990s, a new picture emerged, through the work of Edward Witten and others. Physicists began to see that these 5 string theories were not rivals, but facets of a deeper, more fundamental theory. A theory that lived not in 10 dimensions, but in 11. This deeper theory became known as M theory. The M was never officially defined. It might stand for membrane or mother, or mystery depending on the context. But the principle was clear. M theory was not a 6th string theory. It was the unifying structure from which all 5 known string theories could be derived, as limiting cases. In one limit, where a certain dimension becomes small, M theory looks like Type Ia string theory. In another, where strong-weak coupling duality is applied, it becomes heterotic E8 to KT8. Each known theory can be recovered from M theory, under specific conditions. It is the meta-framework that encompasses them all. M theory introduces a fundamental shift in perspective. In traditional string theories, the basic building blocks are one-dimensional objects, strings vibrating in 10-dimensional spacetime. But in M theory, these strings are just one kind of extended object, among many. The theory also includes 2-dimensional membranes, or 2-branes, and higher dimensional generalizations called p-branes, where p denotes the number of spatial dimensions. A 0-brane is a point particle, a 1-brane is a string, a 2-brane is a membrane, a 3-brane resembles a volume, and so on. In M theory, branes are not added as afterthoughts, they are fundamental constituents. Perhaps the most striking implication is the existence of an 11th dimension. This extra dimension is not merely a mathematical artifact, it has physical meaning. At low energies it becomes small and curled, effectively invisible. But at high energies or strong coupling, it opens up, and the full 11-dimensional geometry becomes relevant. This 11th dimension allows for richer topologies, more complex brane configurations, and new kinds of dualities that were inaccessible in 10-dimensional string theory. It also offers a possible resolution to some of the inconsistencies that arise when attempting to include gravity in a purely string-based framework. One of the most famous manifestations of M theory is its connection to 11-dimensional supergravity. This is the low-energy limit of M theory, a classical field theory that describes gravity, fermions, and gauge fields in 11 dimensions. It was discovered in the 1970s, but only decades later was it recognized as the shadow of something deeper, M theory, in its classical approximation. At higher energies, this supergravity description breaks down, and the full quantum structure of M theory must take over. But the link is important. It tells us that M theory is not arbitrary. It reproduces known physical theories in appropriate limits. M theory also allows for novel solutions that are not naughtily accommodated within 10-dimensional string theory. Among them are M2 branes and M5 branes, the analogues of strings and D-branes, but extended across different numbers of dimensions. These branes play a key role in constructing dualities, building gauge theories, and modeling black hole microstates. In fact, much of the black hole entropy calculations that match string theory predictions with Hawking's results are more naturally expressed in M theory. The extra-dimensional freedom and brane complexity allow for richer microstate counting, Another key contribution of M-theory is its connection to F-theory, a geometric extension of Type 1IB string theory that incorporates varying axiodilaton fields through an auxiliary 12-dimensional space. While F-theory is not a separate theory, it draws heavily on M-theory's higher dimensional structure and helps in constructing compactifications with realistic gauge groups and chiral matter. This brings us to a practical question. Can M-theory make contact with the real world? Can it provide a path to embedding the standard model of particle physics in a consistent quantum gravity framework? The answer, tentatively, is yes, but with caveats. M-theory compactifications on G2 manifolds, a special class of 7-dimensional spaces with exceptional holonomy, have been shown to produce 4-dimensional physics with supersymmetry, gauge interactions, and chiral fermions. G2 manifolds are complex and difficult to construct, but they offer hope for building phenomenologically viable models. They avoid some of the instabilities that plague other compactifications, and their moduli can potentially be stabilized using known mechanisms. Still, many questions remain. We lack a complete non-perturbative definition of M-theory. Unlike the string theories, which have worldsheet formulations, M-theory resists simple quantization. It is known primarily through dualities, limits, and effective field theories. Attempts have been made to formulate M-theory in terms of matrix models such as the BFSS, Banks-Fischler-Schenker-Susskind model, which describes M-theory in light cone coordinates as the large n limit of a matrix quantum mechanics. These models offer insights, but they remain incomplete. Nevertheless, M-theory provides something profound. It brings coherence to the patchwork of string theories. It offers a broader canvas on which to paint a unified picture of quantum gravity, gauge theory, and the origin of spacetime. Its 11-dimensional structure hints that the universe may be richer than our current formulations suggest, that space and time are not fixed ingredients, but dynamic constructs emerging from the behavior of extended objects in higher dimensional geometry. And this perspective changes everything. It rephrase our quest, not as a search for individual equations, but for the underlying structure from which all known laws emerge as approximations. Quantum geometry. When space becomes discrete, geometry has long been the language of physics. From the flat planes of Euclid to the curved spacetime of Einstein, our understanding of the universe has always been shaped by the nature of space itself. But as we push to smaller and smaller scales, geometry begins to falter. The smooth continuum we take for granted starts to dissolve under the pressure of quantum uncertainty. At the Planck scale, around 10⁻35 meters, space is no longer continuous. It cannot be subdivided indefinitely. Attempt to probe such scales, and the very act of measurement distorts the geometry. Gravitational energy becomes so concentrated that it creates a tiny black hole, hiding the region from observation. In this realm, the familiar concept of distance breaks down. This is where quantum geometry enters the picture. It is not geometry as we know it, but a discretized, probabilistic structure where classical notions of length and angle are replaced by expectation values and operator spectra. In this framework, space is not a smooth stage but a quantum system, with its own degrees of freedom. String theory approaches quantum geometry, not by replacing space with a lattice, but by enriching its structure through extended objects. A point particle traces a line through spacetime. A string sweeps out a 2-dimensional surface, a worldsheet, whose topology and interaction encode the behavior of particles and forces. This worldsheet is not embedded in a classical background. It interacts with the background dynamically. Fluctuations in the string alter the surrounding geometry, and the geometry feeds back into the string's dynamics. The result is a self-consistent quantum theory of geometry and matter. In this context, geometry is not given, it is calculated. The metric, which defines distances and angles, emerges as an effective field from the sum over all string configurations. It is no longer a fixed backdrop, but a dynamical variable that evolves according to the rules of quantum mechanics. One of the most profound consequences of this is the elimination of ultraviolet divergences. In quantum field theory, point-like interactions lead to infinities when particles scatter at very high energies. These are typically managed through renormalization, a mathematical patchwork. But in string theory, interactions are spread out across the worldsheet. There are no sharp points, no infinite concentrations of energy. The theory is finite by construction, thanks to the geometry of the string itself. Quantum geometry here is not imposed. It is built into the theory's foundations. Beyond this smoothing of interactions, quantum geometry also affects the topology of space. In classical general relativity, topology is fixed. You start with a given shape of space, and it evolves smoothly under Einstein's equations. But in string theory, topology can change. Strings can split and rejoin, and so too can the space they inhabit. Tunnels can form between distant regions. Handles can appear and disappear. Space becomes a dynamic, malleable object. These processes are governed by stringy corrections to the classical action, higher-order terms that become significant at small distances or strong curvatures. These corrections allow for stringy geometries in which the traditional tools of Riemannian geometry are no longer sufficient. In this quantum regime, new mathematical tools are required. One of the most powerful is mirror symmetry. This is a duality between two seemingly different Calabi geomanifolds, 6-dimensional spaces used in compactification. Despite having different shapes, these manifolds yield the same physics. Their topological data, such as the number of cycles, are exchanged. Mirror symmetry reveals that geometry is not unique. Different spaces can encode identical physical information. This insight has deep implications for quantum geometry. It shows that what matters is not the shape of space in a classical sense, but the structure of the quantum fields it supports. This is echoed in non-commutative geometry, a mathematical framework in which the coordinates of space do not commute. In classical geometry, we assume that x times y equals y times x, but in the quantum realm, this is no longer true. In non-commutative geometry, space is described by operators on a Hilbert space. Position becomes a quantum observable. Distances are replaced by spectra of these operators. The fuzziness of space at small scales is not just a heuristic, it is a precise mathematical structure. This framework is compatible with string theory, especially when background fields like the B field are turned on. In such cases, the world volume of D-branes acquires a non-commutative structure. The field theories that live on these branes become non-commutative gauge theories. This connection provides new ways to understand the emergence of geometry from quantum field theory. It also links to developments in matrix models, where the geometry of space is encoded in large matrices and space-time arises from their dynamics. These models, such as the BFSS and IKKT models, describe space as a derived quantity, emerging from the collective behavior of more fundamental non-spatial variables. They suggest that geometry is not primary. It is a consequence of deeper algebraic structures. This is not just mathematical abstraction. In the ADGE-CFT correspondence, the geometry of the bulk can be reconstructed from the entanglement properties of the boundary theory. Distance becomes a function of quantum information. Geometry becomes entanglement. This is captured in the Ryu-Takayanagi formula, which relates the entanglement entropy of a region in the boundary theory to the area of a minimal surface in the bulk. This formula is not just a computational tool, it is a statement about the fabric of space. Quantum geometry, in this context, is defined by patterns of entanglement. It is not a container, it is a process, a network of correlations that give rise to the illusion of locality and shape. Its viewpoint also connects to the study of quantum gravity through loop quantum gravity and spin foam models, which propose a discrete structure of spacetime. While not based on strings, these theories share the goal of quantizing geometry. In these frameworks, space is built from elementary units, quanta of area and volume, represented by spin networks. The evolution of these networks describes the dynamics of geometry. Time becomes a combinatorial process. String theory and loop quantum gravity differ in many respects, but both suggest that the classical picture of geometry as a smooth manifold must be replaced by something fundamentally quantum and discrete. At the heart of all these developments is a shift in perspective. Space is not a passive stage on which physics unfolds. It is a participant, a product of quantum processes, subject to uncertainty, superposition and entanglement. Quantum geometry is still a developing field. We do not yet have a complete theory, but the pieces are coming together, from string worldsheet dynamics to matrix models, from non-commutative spaces to holographic entanglement. A picture is emerging. A picture in which geometry is not fundamental, but emergent, not fixed, but fluid, not given, but built, from vibration, from interaction, from information. String cosmology and the birth of the universe. The origin of the universe is not merely a question of time. It is a question of structure, of law, of emergence. What came before the hot, dense fireball we call the Big Bang? What principles governed its birth? And can we move beyond extrapolation to a genuine theory of beginnings? In classical cosmology, the story starts with general relativity. Einstein's equations, when applied to a homogeneous and isotropic universe, yield a simple but profound result. The universe is expanding. Rewinding that expansion leads to a singularity, a point of infinite density and curvature, where the equations break down. This is the classical Big Bang. But singularities are not solutions. They are symptoms of the theory's failure. A singularity is where general relativity ceases to apply, where quantum effects can no longer be ignored. To move past it, we need a theory that unites gravity and quantum mechanics. We need string theory. String cosmology is the attempt to apply string theory to the largest possible scales to the entire universe. It is a field that bridges the Planck scale dynamics of strings and branes with the sweeping evolution of space-time itself, and it offers new tools for rethinking the origin of everything. In string theory, the basic units are not point particles, but extended objects. This changes the behavior of space-time at small scales. It smooths out the infinities that plague standard cosmology. For example, a string cannot collapse to a point. It has finite size. This gives rise to a minimal length scale, a kind of resolution limit for the fabric of the cosmos. This minimal length has consequences. In certain models, it prevents the formation of singularities altogether. As the universe contracts, it does not shrink to zero volume. Instead, it reaches a minimum size and then undergoes a bounce, transitioning smoothly from contraction to expansion. These bouncing cosmologies replace the classical singularity with a region of high but finite curvature. String interactions remain well-behaved, and spacetime can continue on the other side. One prominent model in this direction is pre-Big Bang cosmology, developed in the 1990s. It proposes that our observable universe emerged from a pre-existing phase dominated by dilaton fields and stringy effects. As time approaches zero from the negative side, the universe contracts, but with increasing coupling strength and curvature. Eventually, this evolution transitions into the standard hot Big Bang phase. Another approach comes from brane cosmology. In these models, our visible universe is a three-brane, embedded in a higher dimensional bulk. The Big Bang is not the beginning of spacetime, but the result of a brane collision, a high-energy interaction between extended objects. One version of this idea is the ikparotic scenario. It suggests that two branes, existing in a higher dimensional space, gradually move toward one another. Their collision produces a burst of energy, reheating the branes and generating the conditions for hot Big Bang cosmology. The singularity is replaced by a transition surface. These scenarios are not merely speculative. They make contact with observations. They aim to explain the uniformity of the cosmic microwave background, the absence of relic monopoles, and the near-scale invariance of primordial density fluctuations. In some cases, they offer alternatives to inflation. Inflation remains the dominant paradigm for explaining the early universe. It postulates a period of exponential expansion that smooths out the cosmos and seeds its structure, but the exact mechanism, the identity of the inflaton field, its potential, its coupling to other sectors, remains unknown. String theory provides a natural framework for constructing inflationary models. Fields arising from compactification, such as moduli and axions, can serve as inflaton candidates. Brane-antibrane interactions can produce inflaton potentials with plateau-like features, matching observations from the Planck satellite. This leads to brane inflation, a scenario in which inflation is driven by the motion of branes in the compact space. As a d-brane and anti-d-brane approach each other, their interaction provides the necessary potential energy. When they collide and annihilate, reheating occurs, and the universe transitions into a hot, radiation-dominated phase. These models are constrained by the geometry of the extra dimensions, the tension of the branes, and the fluxes that stabilize the moduli. Calculating these dynamics requires tools from algebraic geometry, string perturbation theory, and effective field theory. Another approach is axion monodromy inflation, where the inflaton is an axion field with a potential that wraps around multiple branches. This allows for large field excursions required for observable gravitational waves while remaining consistent with the compact structure of string theory. These string-based inflationary models are testable, in principle, through their predictions for the scalar spectral index, tensor-to-scalar ratio, non-Gaussianities, and isocurvature modes. Future cosmological surveys may confirm or constrain their viability. Beyond inflation, string cosmology also addresses the problem of initial conditions. Why did the universe begin in a low-entropy, highly ordered state? Why was it so homogeneous, yet seeded with tiny fluctuations? Some scenarios, like string gas cosmology, attempt to explain this through thermodynamic arguments. In this model, the early universe is filled with a hot gas of strings. Only 3 spatial dimensions allow for the annihilation of winding modes, which permits expansion. This may explain why we observe 3 large dimensions, while the others remain compact. This dimensional selection mechanism is a direct consequence of string dynamics. It provides a microscopic origin for one of the most basic features of our universe. Other approaches consider the role of the string landscape. If many vacuum states are possible, then eternal inflation or tunneling processes may populate different regions of space with different cosmological parameters. Anthropic arguments then select the subset where conditions permit complex structures to form. Cosmology in this view becomes a problem of probability distributions over the string landscape. Initial conditions are not uniquely determined, but sampled from an ensemble. Our observable universe is a statistical outcome. While these ideas are still developing, they offer a vision of cosmology that is more than extrapolation. They embed the origin and evolution of the universe within the fundamental framework of string theory. They link the thinnest structures to the smallest vibrations. They show that the early universe was not a singularity, but a regime of rich high-dimensional dynamics, a phase where space, time, matter, and law emerged together from a deeper substrate. And in doing so, they bring us closer to a coherent picture, not just of how the universe behaves, but of where it came from and what principles made it possible in the first place. Strings, actions, and the mystery of dark matter. We see only a fraction of what exists. Galaxies spin too fast to be explained by visible matter alone. Clusters bend light more than luminous mass predict. The early universe, traced through the cosmic microwave background, requires more gravitational influence than ordinary atoms can supply. These clues point to a dominant component of the cosmos, one that neither emits nor absorbs light. This is dark matter. Its name is not an answer. It is a placeholder. We know dark matter exists. We know how much of it there is. About 85% of all matter in the universe. We know how it clumps, how it moves, how it shapes galaxies, but we do not know what it is. In the standard cosmological model, dark matter is cold, meaning non-relativistic during structure formation. It must be stable, electrically neutral, and weakly interacting, but beyond these broad traits, its identity remains unknown. Many candidates have been proposed. The most studied are WIMPs, weakly interacting massive particles, predicted by supersymmetric extensions of the standard model. WIMPs naturally have the right properties. Their relic abundance from early universe freeze-out matches observation, but decades of searches in underground detectors, colliders, and astrophysical observations have yielded no evidence. This lack of detection has shifted attention to other candidates, particles that arise naturally in string theory. Among them, one has stood out for its simplicity, consistency, and cosmic relevance: the axion. Axions were not originally invented to solve dark matter. They emerged from an effort to solve the strong CP problem, a puzzle in quantum chromodynamics. The equations of QCD allow for a term that violates charge parity symmetry, but experiments show no such violation in the strong force. Why not? The axion was proposed by Pedicet and Quinn as a dynamical solution. It is a field that adjusts itself to cancel the CP violating term. This elegant mechanism predicts a new particle, light, neutral, and weakly interacting, a perfect candidate for dark matter. But string theory gives the axion a new life. In compactifications of extra dimensions, axion-like particles emerge naturally. They arise from the reduction of higher dimensional gauge fields. and form a ubiquitous part of the moduli spectrum, the set of scalar fields describing shape and size of the hidden compact space. These string axions share the key properties of the QCD axion. They are pseudo-scalars, shift-symmetric, and their interactions are suppressed by a high-energy scale, typically the string scale or compactification volume. Moreover, string theory doesn't predict just one axion, it predicts many. This is known as the axiverse, a landscape of axion-like particles with a wide range of masses and decay constants. Some may be ultralight, with masses around 10 Fe-32 eBOs, producing wave-like behavior on galactic scales. Others may be heavier, contributing to the dark matter abundance in traditional ways. This axiverse opens a rich phenomenology. Ultralight axions could suppress small-scale structure formation, solving tensions in cold dark matter simulations. They can form Bose-Einstein condensates, creating solitonic cores in galaxies. They affect the polarization of the cosmic microwave background, produce oscillating signals in atomic clocks, and induce weak forces in spin alignment experiment. Their interactions are so faint that they evade detection by traditional WIMP searches, but dedicated experiments like ADMX, Casper, and Abracadabra target their unique couplings to photons and nuclear spins. Some use resonant cavities, searching for axion-induced oscillations in magnetic fields. Others look for transient signals from axion clumps passing through Earth. Axions also play a role in inflation. In models of axion monodromy, inflation, an axion field serves as the inflation, its potential extended across multiple branches due to string-theoretic effects. This provides large field excursions compatible with observable gravitational wave production. In this way, the axion is not just a dark matter candidate, it is a bridge between the smallest scales and the largest structures. It emerges from the compactification of hidden dimensions, and it helps drive the accelerated expansion of the early universe. Axions are not the only string-derived dark matter candidates. Moduli fields, scalar fields arising from extra dimensions can also contribute. But these pose challenges. If they decay too late, they disrupt nucleosynthesis. If they decay too early, they fail to reheat the universe. These constraints are known as the moduli problem. Axions, by contrast, are more benign. Their production mechanisms, such as vacuum misalignment, do not require thermal equilibrium. They arise naturally, without the need for finely tuned couplings. In many compactifications, the decay constants of axions are set by the size of cycles in the extra dimensions. These are geometric quantities, and their distribution reflects the shape of the string landscape itself. This makes axion physics a powerful probe of the geometry of hidden dimensions. By measuring axion properties, we indirectly observe the structure of the compact space. It is a form of geometric spectroscopy, bridging particle physics and string theory's extra dimensions. There are also hidden sectors, entire sets of particles and forces that do not couple to the standard model directly, but arise from other stacks of d-branes in the compactified geometry. These sectors can contain stable particles, dark photons, or neutralinos, all of which can act as dark matter. Interactions between our visible sector and these hidden sectors can occur via kinetic mixing, through heavy mediators, or through gravitational coupling. These portals offer other experimental signatures, from deviations in gravity at submillimeter scales to missing energy events at colliders. But axions remain the most elegant. They are minimal. They are motivated by existing theoretical problems. They naturally arise in large numbers from string theory, and they produce observable effects that are now being targeted by a new generation of high-precision instruments. This is a major shift in how we approach dark matter. We are no longer constrained to single candidate theories. We can now explore entire spectra of possibilities, populations of dark matter particles with different masses, interactions, and cosmological histories. String theory makes this possible. It supplies a natural framework for producing a multi-component dark sector. It links the identity of dark matter to the geometry of space itself, and it challenges us to think beyond the standard model. In doing so, it turns the search for dark matter into something more than a particle hunt. It becomes an investigation into the architecture of the universe, the topology of the compact dimensions, and the vibrational modes of unseen fields. And with each constraint, each non-detection, each whisper of a signal from the deep sky or a precision lab. We narrow down the map, we bring the invisible into view, extra dimensions, and the shape of the hidden universe. To understand why extra dimensions are required, we must go back to the mathematics of string theory. When physicists tried to quantize the simplest version, the bosonic string, they found something strange. The equations worked only in 26 dimensions. Later, when supersymmetry was included, the number dropped to 10. Not because anyone wanted it to be that way, but because the mathematics demanded it. This isn't a guess, it's a result. A kind of internal logic, like the way a triangle must have 180 degrees. If you remove these extra dimensions, the consistency of the theory collapses, anomalies appear, predictions become meaningless. The theory simply stops working. So if the universe truly has 10 dimensions, why do we only see 3 of space and 1 of time? The answer lies in compactification. The idea is that 6 of the spatial dimensions are curled up so tightly that they are effectively invisible at low energies. It's like looking at a garden hose from far away. You see a long, thin line, just one dimension. But up close, you notice the hose is cylindrical. There's a hidden circular dimension wrapped around the visible length. Now imagine the same principle applied at a microscopic scale, not to a hose, but to the very fabric of space itself. These hidden dimensions are not random. They have structure, they have geometry, they have shape, and their shape determines the physics we observe. This is one of the most astonishing ideas in theoretical physics. The laws of nature, the types of particles, the forces between them, even the constants of nature are determined by the geometry of the compact dimensions. So what shape are these hidden dimensions? That's where the math gets deep. The most studied possibilities are known as Calabi-Yau manifolds. These are complex, 6-dimensional shapes that satisfy a set of specific mathematical conditions. They are Ricci flat, meaning they have no net curvature, and they preserve a fraction of supersymmetry. But don't let the technical words fool you. These shapes are not arbitrary. They are rich, intricate, like origami folded in 6 directions at once. They contain holes, twists, handles, and multi-dimensional cycles around which strings can wrap. And when strings vibrate in a space like this, their modes of vibration, the spectrum of possible energies and interactions, depend on the topology of the manifold. In other words, the very type of particles we observe, quarks, electrons, photons, emerge from the way strings move in a folded, invisible space. This is why string theorists care so much about the geometry of extra dimensions. It's not abstract, it's not decorative, it's the blueprint for the observable universe. But there isn't just one Calabi-Yau manifold. There are millions, perhaps even an infinite number. Each corresponds to a different vacuum state, a different low-energy physics, a different possible universe. This vast collection of possibilities is called the string landscape. Each point in this landscape represents a different way to compactify the extra dimensions. Different shapes lead to different gauge symmetries. Different symmetries lead to different particle content. And all of this emerges not from tweaking equations, but from the underlying geometry in which the strings reside. Let's take a moment to consider how radical this is. Imagine a universe where the Higgs boson doesn't exist. Not because it was left out, but because the shape of space doesn't allow that mode of vibration. Imagine a world without electromagnetism, because the compact geometry didn't permit a massless spin-1 field. It's as if the laws of physics are written in the folds of origami. Twist the geometry one way, you get our universe. Twist it another way, you get something entirely different. This is both powerful and humbling. Powerful, because it suggests a path to unifying all known forces under a single geometric umbrella. Humbling, because it implies that our universe may be just one of many. A statistical point in a vast configuration space. Compact dimensions can also support fluxes, field lines wrapped around internal cycles. These fluxes help stabilize the geometry, preventing it from collapsing or deforming. They also contribute to the energy content, shaping the vacuum state and influencing cosmological evolution. There are even higher dimensional analogues of Calabi-Yau spaces, used in extensions like M-theory. These include 7-dimensional manifolds called G2 holonomy spaces. They serve a similar role, providing a compact backdrop for membranes and five branes to vibrate and interact. In all these cases, the central theme remains the same. The physics we observe is not just determined by fields and equations, but by the underlying shape of dimensions we cannot see. One of the grand goals of string theory and its extensions is to find the right compactification, the one that reproduces the standard model, that stabilizes the moduli, that explains dark matter, and that allows inflation or bouncing cosmologies. But it's not just about finding the right solution, it's about understanding how the properties of geometry translate into observable consequences. This has led to the birth of an entire subfield, string phenomenology. Here, physicists use tools from algebraic geometry, topology, and number theory to scan through the landscape, to classify possible manifolds, and to compute the physical implications of their geometric features. It's a difficult task. The space of Calabi-Yau manifolds is vast. Their moduli spaces, the parameters describing size and shape, can be multidimensional and filled with complex transitions. There are even dualities that relate one manifold to another. A famous example is mirror symmetry, which connects two different Calabi-Yau spaces, such that the physics remains unchanged. What looks like a hole in one appears as a twist in the other. This symmetry has not only advanced physics, but has revolutionized parts of pure mathematics. It has inspired insights into enumerative geometry, modular forms, and category theory. In this way, the search for hidden dimensions has enriched not only our understanding of the universe, but also our understanding of mathematics itself. And so, we find ourselves in a strange position. We cannot see these dimensions, we cannot reach into them, but we can infer their existence by the shadows they cast on our reality. The strength of gravity, the masses of particles, the charges and couplings of fundamental fields all may be traced to the geometry of a space curled up beyond the limits of direct observation. And as experiments push forward, as we explore the cosmic microwave background, gravitational waves, and high-energy particle collisions, we may begin to gather clues about the unseen structure beneath the skin of reality. Because in string theory, space is not a passive stage, it is a dynamic, structured entity. It is a participant. It shapes and is shaped by the objects that move within it. And when that space includes extra dimensions, the consequences are profound. They determine what exists, they determine what can exist, and they suggest that our observable universe is only the visible tip of a far richer reality. Compactification and the moduli problem. In every geometric shape there are degrees of freedom. A circle has its radius, a cylinder has its height and circumference. A donut, a torus has its inner and outer rings. And when we move from simple shapes to Calabi-Yau manifolds, the number of these freedoms explodes. In string theory, these freedoms are called moduli. They are parameters that describe the size, shape, and structure of the compactified extra dimensions. Each Calabi-Yau manifold comes with hundreds, sometimes thousands of moduli fields. They are massless, scalar fields in 4 dimensions, and they pose a deep challenge. At first glance, they seem benign, just mathematical variables, but in the context of physics, moduli behave like real particles. They carry energy, they have dynamics, and in the early universe they can dominate the evolution of space and time. Picture the early universe just after inflation. As the inflation decays, the universe reheats, producing particles, radiation, and structure. But if moduli are present, they may not decay immediately. They can oscillate, they can dominate the energy density, and if they decay too late, after nucleosynthesis, they destroy the delicate balance required for forming light elements. This is the cosmological moduli problem. If moduli decay too slowly, they inject entropy at the wrong time. They dilute the abundances of helium and deuterium. They ruin the precision with which we understand the early universe. If moduli decay too quickly, they may destabilize the vacuum. Their decay products can cause dangerous relics, gravitinos, axions, or exotic fields to flood the universe with unwanted energy. This tension places tight constraints on any realistic compactification. It demands that moduli be stabilized given masses frozen into place, anchored so they do not roll and dominate cosmic evolution. But stabilization is difficult. The shape of the Calabi-Yau is not rigid. Its moduli space is like a vast valley with many ridges and paths. You need a mechanism, a kind of energetic landscape to fix the moduli at specific values. One approach involves fluxes by threading the internal dimensions with magnetic-like fields, known as NS, and RR fluxes. One can generate a potential that stabilizes some of the moduli. This is known as the Giddings-Kakaru-Polchinski mechanism. In JKP compactifications, fluxes are used to fix the complex structure moduli and the dilaton. These determine the shape of the manifold and the string coupling respectively, but the Kähler moduli, which determine the size of cycles, remain unfixed. To stabilize these, one turns to non-perturbative effects. These include gaugino condensation on D branes and Euclidean D3 instantons, which generate corrections to the superpotential. These corrections create a potential for the Kähler moduli, and by balancing the flux-induced superpotential with these non-perturbative contributions, one can achieve stabilization. This was formalized in the KKLT scenario, named after Kocherou, Kalash, Linde, and Trivedi. It provides a framework in which all moduli are stabilized, and the vacuum energy can be tuned to produce a small positive cosmological constant. In KKLT, after moduli are stabilized, an anti-D3 brane is added to uplift the potential, raising the vacuum energy from negative AdS to positive DS. This allows for a universe that expands at late times, a requirement for matching our observation. But KKLT is not the only approach. Another framework, called the Large Volume Scenario, LVS, achieves stabilization by creating an exponentially large internal volume. In LVS, the potential is minimized at a point where the Kähler moduli yield a vast compact space, orders of magnitude larger than the string scale. This has interesting consequences. It naturally generates a hierarchy between the Planck scale and the weak scale. It suppresses dangerous couplings, and it provides a mechanism for moduli to be heavy enough to decay early, avoiding the cosmological moduli problem. But all these solutions come with trade-offs. They require specific configurations, fine-tuned fluxes, careful balancing of terms. They also leave open questions about the full consistency of the theory, especially in the presence of quantum corrections. There's also the question of vacuum selection, with so many possible compactifications, each corresponding to different vacuum states. How does the universe choose? Why this set of moduli values, this volume, this curvature? Some suggest the answer lies in anthropic selection. We observe this vacuum because it supports life, structure, and observers. In the string landscape, our universe may be one of countless others, a bubble in a multiverse of compactifications. Others seek a dynamical explanation. Perhaps certain vacua are more stable, more likely to emerge from Minas conditions, or more natural within the evolution of the early universe. But the moduli problem is not only cosmological, it is also phenomenological. Unstabilized moduli can mediate new forces. They can lead to violations of equivalence principle, variations in fundamental constants, or fifth force effects. Experiments have placed tight bounds on such effects. The moduli must be stabilized, with masses above certain thresholds, often in the multi-TeV range or higher, to evade detection. This pushes models toward heavy moduli, high-scale supersymmetry breaking, and suppressed couplings. At the same time, moduli stabilization affects low-energy physics. It determines the soft terms, the spectrum of superpartners, and the structure of the visible sector. In this way, the geometry of the extra dimensions and the stabilization of their moduli feed directly into the properties of the particles we observe in laboratories. This is the essence of string phenomenology, linking the geometry of the compact space to testable predictions in 4 dimensions. But the moduli are more than obstacles, they are messengers. They tell us how the compact dimensions breathe, how they warp and twist, how they embed within the full theory. And in that sense they are also opportunities. If we can detect them through cosmology, particle physics, or astrophysical anomalies, we gain direct access to the hidden geometry of the universe. Some theories suggest moduli could be produced in the early universe and still linger today. They might decay into photons or affect the formation of structure. They might be detectable through dark radiation, CMB distortions, or subtle effects on galaxy surveys. Others suggest that moduli stabilization could leave imprints on inflationary observables, such as the tensor-to-scalar ratio, non-Gaussianities, or spectral tilt. Each of these is a clue, a breadcrumb on the trail, leading to a fuller understanding of the string compactification, because ultimately, compactification is not a mathematical trick, It is a physical process. It is the way string theory connects its higher dimensional framework to the four-dimensional world we see. It is how strings give rise to protons and electrons, light and gravity, matter and mind. And the moduli, as troubling as they are part of that bridge. They are the variables of the hidden space, the coordinates of the invisible. To solve the moduli problem is to stabilize reality itself, to give structure to the unknown, and to bring the language of geometry into the world of physical law. Warped compactifications and the hierarchy problem. In the everyday world, the forces of nature feel balanced. A refrigerator magnet easily lifts a paper clip, defying the gravitational pull of the entire planet. This is not because the magnet is strong, it's because gravity is unbelievably weak compared to the other fundamental forces. This mismatch is known as the hierarchy problem. Why is the gravitational force 40 orders of magnitude weaker than the strong nuclear force? Why is the Planck scale, where gravity becomes strong, so vastly higher than the electroweak scale, where particles acquire mass? In particle physics, this hierarchy is unstable. Quantum corrections tend to drive the Higgs boson mass up to the Planck scale, unless there is an intricate mechanism to protect it. This fine-tuning feels unnatural. It cries out for explanation. In 1999, Lisa Randall and Raman Sundram proposed a radical solution. They suggested that the hierarchy might not be a coincidence or a flaw in the standard model, but a consequence of geometry. In their model, our universe is a four-dimensional brane, embedded in a higher dimensional space-time, specifically, a five-dimensional universe with a single extra spatial dimension, which is warped rather than flat. The warping is not metaphorical. It appears in the metric, the mathematical object that defines distances in space-time. The five-dimensional space-time has the form del squared equals e to the power of minus 2k r absolute y times the four-dimensional Minkowski metric plus dy squared. Here, y is the coordinate of the extra dimension, r is its radius, and chi is a curvature scale set by the bulk cosmological constant. The exponential warp factor, e to the minus 2k ry, shrinks energy scales as you move along the extra dimension. In this setup, the geometry is a slice of anti-de Sitter space, a space-time with constant negative curvature. The extra dimension is bounded by two branes, the Planck brane, where gravity is localized, and the TeV brane, where the standard model fields reside. Due to the warp factor, a physical mass m0 on the TeV brane appears to observers on the Planck brane as m equals m0 times e to the minus k r pi. This exponential suppression can explain why the electroweak scale is so much lower than the Planck scale without fine-tuning. It's not a miracle, it's the shape of space. This insight revolutionized how physicists think about extra dimensions. It showed that geometry could solve problems once thought to require new symmetries or new particles. The Randall-Sundram model, RS1, was quickly generalized. Variations allowed different fields to propagate in the bulk, or localized at different positions along the extra dimension. And then string theorists asked, can warped geometries like this emerge naturally from string theory? The answer, remarkably, is yes. In 2001, Giddings, Kakru and Polchinski demonstrated that by introducing fluxes in type IB string theory, one can generate warped compactifications. These fluxes, NS and RR fields, thread through the cycles of the Calabi-Yar manifold and their energy curve space-time. In regions where the fluxes are strong, the geometry pinches, forming a throat. The most famous example is the Klebanov-Strassler throat, a warped region based on a deformed conifold. It provides a smooth, non-singular solution with large warping. In such warped throats, the warp factor behaves like e to the power of minus 2a of r, where a of r is a function of the radial coordinate along the throat. Near the bottom of the throat, the warp factor becomes exponentially small. Energy scales are redshifted. If the standard model is placed at the bottom of the throat, its characteristic energy scales are suppressed relative to the Planck scale. This provides a natural explanation for the hierarchy within string theory. Warped compactifications also help stabilize moduli. The fluxes generate a potential that fixes the complex structure moduli and the dilaton. The warping helps suppress corrections, enhancing control over the theory. Moreover, Warped geometries offer rich phenomenology. They can accommodate chiral matter, localized gauge sectors, and mechanisms for supersymmetry breaking. For example, placing an anti-D3 brane at the bottom of a warped throat can break supersymmetry in a controlled way. The warping redshifts the brane's tension, leading to a small vacuum energy, a candidate for dark energy. This idea lies at the heart of the KKLT scenario. It combines flux compactification, warping, and non-perturbative effects to produce a stable, de Sitter-like vacuum with all moduli fixed. Warped throats also have cosmological applications. They provide natural settings for brane inflation, where inflation is driven by the motion of branes in warped space. In these models, a D3 brane moves toward an anti-D3 brane located at the bottom of a throat. The attractive potential between them drives inflation, while the warping flattens the potential, making it more consistent with observations. Such models can produce distinctive signatures, cosmic strings, non-Gaudiumacities, or even extra-dimensional relics. But warping is not a panacea. It complicates calculations. It affects how supersymmetry breaking is mediated to the visible sector. It influences the dynamics of reheating, moduli stabilization, and the cosmological constant. Still, the geometric elegance of warping is undeniable. It shows that the fabric of space is not merely a container for particles and fields, but an active participant in shaping physical law. Warped geometry also relates to the Adaius-CFT correspondence, the duality between gravity and anti-de Sitter space, and a conformal field theory on its boundary. In this picture, a warped throat corresponds to a strongly coupled gauge theory, flowing from the ultraviolet to the infrared. The bottom of the throat represents confinement, the dual description of QCD-like behavior. This duality provides tools for studying phenomena like quark-gluon plasmas, holographic superconductors, and entanglement entropy. In string theory, warped compactifications bring together geometry, field theory, and cosmology. They unify problems that once seemed separate, like the hierarchy problem and the nature of gravity, under a single geometric lens. They also guide searches for new physics. If extra dimensions are warped, they might leave imprints on collider signatures, such as resonances, missing energy, or deviations from Newton's law at short distances. Experiments at the Large Hadron Collider have looked for signs of Randall-Sundrum gravitons, massive spin-2 particles that arise in warped models. So far, the results are negative, but constraints are improving. Future colliders, precision tests of gravity, and cosmological observations may one day confirm whether our universe truly contains warped extra dimensions. Until then, warping remains one of the most promising ideas linking string theory to observable phenomena. It tells us that the weakness of gravity may not be a flaw, but a clue, a pointer to a richer structure beneath the skin of space-time. That the universe is not flat, but curved in secret places, that energy scales, like rivers, can be bent by the hills and valleys of higher dimensions, and that by following these bends, we may find answers to the questions that have eluded physics for decades. The hierarchy problem once seemed like a mystery of particle interactions. Warped compactification reframes it as a story of geometry, a question not of mass, but of scale, not of force, but of shape. And in that story, the weakness of gravity becomes not a bug, but a feature, written into the warped grain of the extra dimensions that may surround us still. Brane worlds and the multiverse, a membrane, a surface, a brane. In the language of string theory, a brane is not an abstraction. It is a real, physical object, one that can stretch across space, vibrate, carry charges, and warp the dimensions around it. We may live on such a brane, not in empty space, but within a higher dimensional arena, where our entire universe is confined to a membrane, floating in a broader cosmos we cannot touch. This is the idea of brane worlds, a universe that's not the whole, but just a slice. And when there are many branes, when there are countless ways to compactify, fold, and twist the extra dimensions, we arrive at something even larger, the multiverse. A vast landscape of possible universes, each with its own laws, its own vacuum, its own fate. And to see how this works, imagine a higher dimensional bulk, a space of more than 4 dimensions. Within this bulk, float multiple branes of various dimensionality. Some might be parallel to ours, others tilted at angles. Each brane can host a universe with its own particles and forces confined to it. Gravity, carried by closed strings, propagates through the entire bulk. But gauge forces, electromagnetism, the weak force, the strong force, are confined to the branes. This explains why gravity is weaker. It leaks into the extra dimensions, while the other forces cannot. In such a picture, our visible universe is a four-dimensional brane, embedded in a higher dimensional bulk. The extra dimensions may be large or small, flat or warp, but the essential point is that we are stuck on a membrane, unable to move off it. This brane world scenario radically reframes cosmology. When branes move, they can collide. These collisions can produce energy, potentially the Big Bang itself. As branes approach, tension builds. At the moment of contact, energy is released into the brane-localized fields, igniting hot, dense conditions and triggering cosmic expansion. This is the basis of the ekplerotic and cyclic models. Rather than a singular beginning, they propose a periodic sequence of brane collisions and separations. Each collision is a cosmic reset, a new Big Bang. The universe cycles through birth, expansion, contraction, and renewal, potentially ad infinitum. Each cycle may have different properties. The shape of extra dimensions could evolve, moduli fields may shift, the cosmological constant may change its value. Over time, the multiverse of brane worlds could sample a wide range of physical conditions. In this framework, our particular universe is one among many brane world universes, selected not by uniqueness, but by anthropic necessity. Only those universes where constants fall within narrow ranges allow structure, chemistry, and life. Observers naturally find themselves on branes with the right conditions. This idea extends the string landscape to a brane landscape, an even richer tapestry of possible realities. Not only do we have many ways to fold extra dimensions, but many ways to arrange branes and fluxes in the higher dimensional bulk. Each arrangement defines a vacuum state, a stable or metastable minimum of the full potential. Transitions between vacua can occur through tunneling. Bubbles nucleate, carry new physics within them, and expand. Our observable universe could be the interior of one such bubble. This is the mechanism behind eternal inflation, where inflation never ends everywhere. While inflation halts inside some bubbles, creating pocket universes like ours, it persists elsewhere, continuously spawning new regions with varied physical parameters. The multiverse thus becomes a dynamic, ever-growing ensemble of pocket universes, each a brane or bubble, with its own compactification, its own particle content, its own low-energy laws. From this vantage, questions about fundamental constants become questions about distribution functions. What fraction of pocket universes have a cosmological constant low enough for galaxy formation? What fraction allows stable atoms? What fractions support carbon-based chemistry? Calculating these probabilities requires a measure, a way to regulate the infinities in eternal inflation. This measure problem remains unsolved. Different proposals, moving volume, scale factor, cutoff, like cone time, yield different statistical predictions. Which is correct? May require new physics or a deeper understanding of quantum cosmology. Despite these challenges, the brane world multiverse offers an explanatory paradigm for puzzles that single universe theories struggle to address. It contextualizes fine-tuning as a selection effect. It redefines the goal of fundamental physics from unique prediction to statistical explanation. Of course, the multiverse is controversial. Some argue it lies beyond empirical science, untestable, unfalsifiable, but brane world models make contact with observation. They predict signatures in colliders, in gravitational wave backgrounds, in cosmic microwave background anisotropies. For example, graviton-Kaluza Klein modes, in large extra dimensions, could produce missing energy. At the Large Hadron Collider, they could alter Newton's law at sub-millimeter scales, detectable by precision force experiments. Brane collisions could leave imprints in primordial gravitational waves. Their spectrum could reveal the shape and warping of the bulk geometry. Cosmological observations of the CMB and large-scale structure constrain the number and size of extra dimensions. They limit the energy lost to bulk gravitons during supernova and early universe dynamics. These constraints are growing tighter, yet the possibility of discovering extra dimensions remains open. Beyond observational signatures, Brainsworld ideas have inspired developments in quantum gravity. Holographic dualities between brane configurations and lower dimensional field theories continue to deepen our understanding of entanglement, emergence, and space-time reconstruction. In the Agile CFT correspondence, stack D3 branes give rise to Diridaceous 4 super Yang mills on the boundary and Agile in the bulk. This duality provides a laboratory for studying strongly coupled gauge theories, black hole thermodynamics, and quantum chaos. Generalizations to less symmetric setups with wrapped branes, flux compactifications, and nonconformal field theories extend holography into realms closer to our own universe. Thus, brane worlds are not just cosmological curiosities, they are tools for probing the deep connection between gravity, geometry, and quantum physics. In the broadest sense, the multiverse is the ultimate brane world. It is the collection of every conceivable brane configuration, every compactification, every vacuum. It is the space of all possible laws. Whether the multiverse is real or remains a theoretical construct yet to be tested, brane world ideas have reshaped our quest for a fundamental theory. They have shown us that reality may be far richer than our four-dimensional intuition allows. As we explore further through theory, through experiment, through cosmic observation, we may one day glimpse the hidden branes and pocket universes that surround us in the vast multiverse. Until then, we continue our journey along the membrane of our own world, peering into the bulk and dreaming of the brane worlds that lie beyond. String compactifications and low-energy phenomena. The universe we experience daily, the solidity of matter, the warmth of sunlight, the pull of gravity, is defined by low-energy phenomena. But beneath these familiar interactions, far beyond the limits of perception, exists a deeper reality from which these everyday forces emerge. In string theory, this deeper reality is woven from vibrating strings, moving in extra dimensions. To connect that hidden world with our observable universe, we use a powerful idea called compactification. Compactification is the art of folding unseen dimensions into tiny, intricate shapes that dictate the behavior of everything we know. At high energies, the universe is symmetrical and unified. Forces blend together, particles are indistinguishable. But as energy decreases, as temperature falls, symmetry breaks, the universe cools, and complexity arises. Particles gain distinct masses, forces separate, the rich tapestry of reality emerges, shaped by how these extra dimensions are compactified. The mathematics of compactification is precise, subtle, and beautiful. It begins with 10-dimensional string theory, the simplest consistent quantum theory of gravity. To reach our 4-dimensional world, 6 spatial dimensions must be curled into shape so small they remain invisible to even our most powerful microscopes. These shapes, these extra-dimensional spaces, are often Calabi-Yau manifolds, named after mathematicians Eugenio Calabi-Yau and Xing-Tung Yau. They possess remarkable properties that make them ideal for string compactification. They are compact, richly flat, and preserve a fraction of supersymmetry, a symmetry connecting bosons and fermions. Calabi-Yau manifolds come in countless varieties. Each has its own topology, a unique combination of holes, twists, and cycles. Strings winding around these cycles produce distinct vibrations, and each vibration corresponds to a different particle type or force interaction in our 4-dimensional universe. In essence, the shape of the Calabi-Yau manifold is like the musical instrument upon which the universe's symphony is played. Change the shape, and the notes, the particles, masses, forces, change as well. This connection between geometry and low-energy physics is both profound and practical. It allows string theorists to explore fundamental physics by studying complex geometries, to ask questions about electrons, photons, and quarks by examining the intricate structures of hidden dimensions. But compactification is more than geometry. It involves fields and fluxes, energy distributions threading through extra-dimensional spaces. These fluxes generate potentials that help stabilize the shapes of extra dimensions. They ensure that our universe remains steady and predictable, avoiding uncontrolled growth or collapse of compactified space. When these fluxes are switched on, they generate vacuum states, the lowest energy configurations for string theory fields. These vacuum states, called vacua, are critical for physics. Each vacuum defines a distinct set of physical constants, particle spectra, and low-energy interactions. This multiplicity of vacua creates a vast landscape of possibilities. Different compactifications yield different universes, each with its own physical laws and parameters. Our universe is but one possibility, one vacuum chosen by chance, necessity, or deeper principles yet undiscovered. This idea, known as the string landscape, has profound implications. It suggests our universe's observed constants may not be unique or fundamental. Instead, they might be statistical outcomes, selected because only certain combinations allow stable matter, galaxies, and observers. Compactification thus transforms the quest for fundamental physics. Instead of seeking a unique set of laws, we explore a vast space of possibilities, asking statistical questions about typicality, likelihood, and anthropic selection. But compactification is not purely theoretical. It produces tangible, testable predictions. For instance, it determines how supersymmetry, if it exists, might manifest at accessible energies. It influences dark matter candidates, such as axions or neutralinos, whose detection experiments tirelessly pursue. Compactification also shapes cosmology. The structure of the extra dimensions affects early universe phenomena, inflation, reheating, and the cosmic microwave background. The presence of moduli fields controlling the shapes and sizes of compact spaces can alter nucleosynthesis, dark radiation, and structure formation. These moduli, if they remain unstabilized, lead to serious problems, known as the cosmological moduli problem. Unstabilized moduli fields can dominate the universe's energy and disrupt its delicate balance. Thus, moduli stabilization is essential, and achieving it requires careful engineering of compactification scenarios with fluxes and branes. Branes, extended objects in string theory, also enrich compactifications. They provide locations where gauge theories, like the Standard Model, can naturally reside. The position and geometry of branes within compact spaces dictate particle spectra, masses, and couplings, directly connecting hidden geometry to observable physics. This connection has sparked extensive research in brane world phenomenology, where models place our universe on a brane embedded in a warped, extra-dimensional space. Such scenarios solve puzzles like the hierarchy problem, the vast difference between the weak scale and Planck scale, by geometric means. Warped compactifications, such as the Randall-Sundrum model, provide elegant explanations for the weakness of gravity. The warped geometry of extra dimensions exponentially suppresses mass scales, naturally generating hierarchies without excessive fine-tuning. These warped geometries also appear naturally within string compactifications, Klebanov-Strassler throats, regions of strong warping, formed by fluxes in Calabi-Yau manifolds, illustrate how gravity's weakness can be traced back to the shape of hidden dimensions. Testing these predictions pushes experimental physics to its limits. High-energy colliders search for signals of extra dimensions, such as missing energy or resonances from Kaluza-Klein modes, heavy particle excitations emerging from extra-dimensional momentum. Precision gravitational tests probe deviations from Newton's law at tiny distances, searching for hints of compactification scales. Cosmological observations track dark radiation, axion fields, or moduli decay products to reveal subtle signatures of string-scale physics. Yet the landscape is immense. Countless compactifications exist, each predicting slightly different physics. Distinguishing among them requires both theoretical insight and experimental ingenuity. It challenges physicists to find universal features, robust predictions, and sharp observational discriminators. One promising direction is connecting compactifications to inflationary scenarios. Specific compactifications predict distinct inflationary signatures, gravitational wave spectra, non-Gaudianities, and patterns of cosmic strings, which upcoming cosmological experiments can test. Thus, Compactification is more than abstract geometry. It is a bridge, connecting fundamental strings to our low-energy world, tying extra-dimensional shapes to experimental observables, and linking quantum gravity to cosmology and particle physics. Ultimately, understanding compactification is key to uncovering deeper principles. Principles that select among countless possible worlds. Principles that explain why our universe appears as it does. Principles that reveal the structure hidden beneath familiar phenomena. This ongoing journey is one of discovery, exploration, and synthesis. Through compactification, we glimpse the unity beneath diversity, the hidden simplicity underlying complexity. As we continue, we learn that the universe's most familiar aspects, the stability of atoms, the solidity of matter, the warmth of sunlight, are reflections of hidden geometries, of strings vibrating in unseen dimensions, of compactifications shaped by fluxes and branes. In this way, compactification is the hidden code of reality. Decode it, and we unlock not just the mysteries of strings and dimensions, but the very essence of the low-energy world, the everyday universe we call home, dualities, and the unity of string theory. Physics has long been guided by symmetry. From the elegant simplicity of rotational symmetry that defines spheres and circles, to the deeper internal symmetries that shape particle interactions, symmetry underpins our understanding of the universe. But string theory introduces something even deeper than conventional symmetries. It introduces dualities. Dualities are profound equivalences between seemingly different physical theories. They reveal that what appears distinct may actually be the same, viewed from another angle. In string theory, dualities are not mere curiosities. They are foundational. They hold the key to unifying the seemingly disparate versions of string theory into one coherent framework, a theory known as M-theory. To appreciate dualities, we must first understand their simplest form, T-duality. T-duality emerges from compactified dimensions, dimensions that loop around themselves like circles. In string theory, strings can wrap around these compact dimensions, and they can also vibrate with momentum around these loops. Surprisingly, a string wrapping around a small circle is physically indistinguishable from a string moving around a large circle with quantized momentum. This equivalence means that a universe with extra dimensions, compactified on a circle of radius r, is identical to one compactified on a circle of radius proportional to 1 divided by r. This remarkable symmetry transforms distances, small into large, large into small. It transforms winding modes into momentum modes. Yet the physics remains unchanged. Observations, experiments, even the laws themselves are preserved under this duality. T-duality thus reveals a fundamental ambiguity in measuring length scales at the smallest dimensions. Below a certain scale, the string scale, the concept of small, loses its meaning entirely. Space becomes quantum foam, and geometry itself becomes fluid. But T-duality is only the beginning. An even more powerful equivalence is S-duality. S-duality relates theories with strong coupling to theories with weak coupling. Coupling measures interaction strength. In electromagnetism, it corresponds to electric charge. In string theory, it measures the string interaction stress. An S-dual transformation takes a strongly coupled theory, where strings strongly interact, and maps it onto a weakly coupled theory, where interactions are gentle and easily calculable. Under S-duality, fundamental strings and solitonic branes interchange roles. Electric and magnetic charges swap places. This duality is especially remarkable in type IB string theory, where the theory's equations are invariant under these strong-weak transformations. Type IB theory is thus self-dual. It is its own dual partner. S-duality profoundly alters our view of quantum theories. It suggests there is no absolute definition of a strongly or weakly interacting theory. Strength and weakness depend entirely on your perspective, the variables you choose, the viewpoint you adopt. Slews, dualities transform once intractable problems into manageable ones. When calculations become impossible at strong coupling, dualities map them onto weakly coupled theories, where approximations and perturbations become simple. This powerful technique extends beyond simple string theories into gauge theories, quantum field theories, and cosmological models. It has led to breakthroughs in understanding black holes, quantum chromodynamics, and even condensed matter physics. Yet even S-duality and T-duality are just special cases of a deeper phenomenon called U-duality. U-duality unifies S-duality and T-duality into a larger symmetry group. It reveals deeper connections between string theories and supergravity theories in higher dimensions. U-duality hints at a hidden, fundamental structure, one that transcends the 5 distinct 10-dimensional string theories. It points toward the existence of an 11-dimensional theory, M theory, which unifies these separate strands into a single tapestry. In M theory, strings become special cases of higher dimensional objects, branes of various dimensions, including membranes and 5 branes. The dualities once connecting different string theories become reflections of different perspectives on this unified theory. In fact, the very existence of M theory was inferred through these dualities. In 1995, Edward Witten showed that by applying dualities, all 5 known string theories are simply different limits of a single 11-dimensional theory, M theory. Under certain conditions, M theory reduces to type Ia string theory, while other conditions yield heterotic or type I theories. All string theories, once thought separate, emerge as shadows, distinct views of a single unified entity. Dualities also offer profound insights into black holes. In classical physics, black holes are regions where gravity is infinitely strong and time seems to stop. But string theory uses dualities to reinterpret black holes in terms of microscopic states, strings, and branes, whose entropy matches exactly with the black hole's area. This microscopic description obtained through dualities resolves long-standing puzzles, including Hawking's famous information paradox. Dualities reveal that information lost inside a black hole may actually be encoded in quantum states of strings and branes, preserving quantum coherence and consistency. Another powerful duality, the ADA-CFT correspondence, has revolutionized physics, proposed by Juan Maldacena in 1997. This duality relates gravitational theories in anti-de Sitter space to quantum field theories without gravity on their lower dimensional boundary. Through ADA-CFT, complex gravitational problems like quantum gravity, black hole physics, and strongly coupled field theories can be mapped onto simpler, non-gravitational theories that we understand well. This duality is a profound step towards solving quantum gravity and understanding space-time emergence. Moreover, ADA-CFT has practical implications in condensed matter physics, nuclear physics, and quantum information science. It provides a toolkit for studying strongly coupled systems like superconductors, quark-gluon plasmas, and quantum entanglement from a new gravitational perspective. At their core, dualities challenge traditional ideas of physical reality. They suggest that concepts we hold fundamental, such as dimension, length, coupling strength, are not absolute, but context-dependent. They are emergent, contingent on the observer's viewpoint. Dualities teach us humility. They warn against believing too strongly in any one description of reality. Instead, they encourage a flexible, open-minded approach to understanding nature. Perhaps most importantly, dualities are guiding us toward a more unified vision of physics. They reveal that what appear to be different phenomena, gravity, quantum fields, black holes, particles, may all spring from a single, coherent framework. String theory, with its intricate web of dualities, offers precisely this framework. It shows how seemingly separate branches of physics can be reflections of a single deeper structure. It provides the language to unify gravity, quantum mechanics, and gauge theories into one harmonious picture. Through dualities, string theory has become more than a theory of strings. It is a theory of unity itself. It represents the idea that beneath diversity and complexity, there is simplicity and coherence. Thus, dualities do more than solve technical puzzles. They guide our philosophical and conceptual approach to physics. They demonstrate the interconnectedness of all things, the subtlety of perception, and the richness of the universe's hidden symmetries. As we continue exploring, dualities will remain at the heart of fundamental physics. They will shape our quest for the ultimate theory, the theory of everything. And in the gentle, elegant way, they unify diverse theories. Dualities teach us a lesson that the deepest truths often lie in seeing connections where none were previously imagined. This is the true power of dualities, not just to unify string theories, but to unify our understanding of nature itself, bringing clarity, harmony, and unity to the mysterious universe in which we live. Gauge gravity duality and the holographic principle. Imagine the universe not as a vast three-dimensional expanse, but as information encoded on a distant two-dimensional surface. Picture reality itself as a hologram, not the flat holograms we see in daily life, but one that captures every detail, every particle, every force, every quantum fluctuation. This radical idea is known as the holographic principle, and at its core lies one of the deepest insights to emerge from modern theoretical physics: the gauge gravity duality, also called the ADES-CFT correspondence, proposed by Juan Maldacena in 1997. This duality relates gravitational theories living in higher dimensional spaces, specifically anti-de Sitter, ADES spacetimes, to lower dimensional quantum field theories, known as conformal field theories, CFTs, defined on their boundary. The correspondence is precise and startling. A theory of gravity in five-dimensional AD space is mathematically identical, dual to a four-dimensional conformal quantum field theory, without gravity defined on its boundary. The physics of gravity in curved spacetime in the interior is perfectly mirrored by the dynamics of strongly interacting quantum fields on the surface. To visualize this, imagine a spherical region of space. Inside the sphere, gravity acts, spacetime curves, black holes form. But according to this duality, all the physics happening within that volume can be entirely described by fields on the sphere's two-dimensional surface. Information encoded on the boundary surface dictates every gravitational phenomenon inside. This is not just a mathematical trick, it is a profound reshaping of reality. The implications of vast, gravity, space, and time may not be fundamental entities, but emergent phenomena arising from deeper quantum information patterns encoded on a lower dimensional surface. Satyobing say, the gauge gravity duality grew from efforts to understand string theory and the behavior of D-branes extended objects within string theory that host gauge theories on their world volumes. By stacking many D-branes, strong gravitational fields form, creating an AD spacetime region around them. Simultaneously, the physics describing the interactions of open strings on these branes defines a quantum field theory. Thus emerged the remarkable insight that these gravitational and gauge descriptions, seemingly unrelated, are actually dual aspects of one unified system. This duality provides a powerful new tool to study gravity in quantum field theory. Traditionally, gravity at quantum scales is notoriously challenging. Quantum gravitational effects are typically inaccessible because gravity becomes strongly interacting, breaking down standard perturbative methods. But through ADS-CFT, strongly coupled gravitational physics is equivalent to a weakly coupled non-gravitational field theory. This makes previously intractable quantum gravity problems accessible, solvable, and comprehensible by translating them into well-understood field theory calculations. Conversely, the duality helps tackle problems in strongly coupled quantum field theories, like quantum chromodynamics, QCD, the theory describing quarks and gluons. These strongly interacting systems are notoriously difficult to handle directly. Yet, through gauge gravity duality, they map onto classical gravitational systems, where solutions are simpler to obtain. This approach, known as holographic QCD, has produced significant insights into phenomena like quark-gluon plasmas observed in particle colliders, explaining properties such as viscosity, energy transport, and thermalization processes with remarkable accuracy. Gauge gravity duality has also impacted condensed matter physics, leading to the emerging field of holographic condensed matter. It provides powerful theoretical frameworks for strongly correlated electron systems, superconductors, and quantum phase transition systems notoriously resistant to traditional analytic methods. In these holographic models, strongly interacting electron systems map onto black holes or exotic gravitational configurations, in higher dimensional ad space. By studying gravitational phenomena like event horizons and temperature gradients, physicists gain deep insight into complex quantum states of matter, such as strange metals and superconductors. At the heart of gauge-gravity duality lies the concept of quantum entanglement. Entanglement, the quantum linkage between particles, where their states remain correlated, regardless of spatial separation, plays a fundamental role in encoding geometry itself. Through AD-CFT, geometric features of spacetime like distance, curvature, and topology are translated into entanglement structures within the boundary quantum field theory. In particular, the Ryo-Takayanagi formula beautifully connects entanglement entropy, the boundary regions, to the area of minimal surfaces in the bulk spacetime. This means geometry can be reconstructed entirely from quantum entanglement. Space and gravity emerge from quantum information patterns. This viewpoint, called the tit-from-qubit perspective, suggests that the fundamental fabric of spacetime is quantum information itself, woven from entangled quantum state. Such insights have profound implications for the nature of black holes and quantum gravity. For instance, gauge-gravity duality has clarified the black hole information paradox, the puzzle of what happens to information falling into black holes. AD-CFT shows explicitly how information is encoded on the boundary, ensuring no information loss occurs. This holographic encoding of information also relates directly to the holographic principle proposed by Jared Hooft and Leonard Susskind in the 1990s. The principle posits that all the information contained within a region of space can be represented entirely by a theory defined on the boundary of that region. The holographic principle originated from studying black hole entropy, where it was observed that entropy scales with the black hole's event horizon area, not its volume, suggesting that the true degrees of freedom of any gravitational system are holographically encoded on lower dimensional boundaries. Gauge-gravity duality provided the first explicit realization of this radical principle. Through AD-CFT, the entire physics inside a bulk region is perfectly captured by quantum fields living on its boundary, a perfect holographic representation of gravitational physics. Today, gauge-gravity duality remains one of the most vibrant areas of theoretical physics. Its power extends across disciplines, from particle physics and cosmology to quantum information theory and condensed matter physics. Researchers are exploring how holography might apply beyond idealized ad spaces. Could our universe, with its positive cosmological constant and accelerating expansion, also admit holographic description? Efforts to generalize gauge-gravity duality to more realistic cosmological spacetimes, such as de Sitter spaces, are ongoing and represent an exciting frontier. Other directions include deeper investigations into the role of quantum entanglement in spacetime emergence. Quantum computational tools are now used to probe these holographic systems, revealing connections between quantum error correction codes, entanglement entropy, and the reconstruction of gravitational bulk spaces from boundary quantum data. The gauge-gravity duality thus represents far more than a theoretical curiosity. It is a fundamental conceptual advance, showing how gravity, space, and time can be emergent phenomena derived from deeper, non-gravitational quantum field theories. It offers a new paradigm in our quest for quantum gravity, where traditional boundaries between gravity and quantum mechanics dissolve, replaced by unified structures based on quantum information, entanglement, and dualities between description. The holographic principle challenges and reshapes our understanding of reality. It suggests a deeper unity between the microscopic and macroscopic, between gravity and quantum theory, between information and geometry. As we continue exploring gauge-gravity duality, we step closer to unraveling the fundamental fabric of our universe. We glimpse the possibility that beneath all complexity, beneath particles, forces, space, and time, lies quantum information, encoded holographically on distant boundaries. And perhaps in understanding this holographic universe, we gain the ultimate insight that the vast cosmos we inhabit, in all its atticus and beauty, is but a shadow, a projection, a perfect hologram emerging from the delicate interplay of quantum fields and gravitational geometry. Holography, entanglement, and quantum information in string theory. When we gaze at the night sky, we sense a vast three-dimensional cosmos, an expansive realm filled with galaxies, stars, planets, and us, a universe of immense complexity. Yet, according to modern physics, This complexity may spring from something surprisingly simple: information encoded on a lower dimensional boundary. This insight emerges from holography, a concept that began as a theoretical curiosity, but now stands at the forefront of physics. In string theory, holography reaches its deepest expression, revealing connections between geometry, gravity, and quantum information. At the heart of holography lies quantum entanglement, a profound, subtle connection between quantum systems. Entanglement allows distant particles to influence each other's states instantaneously, no matter how far apart they are. This phenomenon, once considered mysterious and even paradoxical, now provides the fundamental thread weaving together space and time. To grasp how holography and entanglement intertwine, we must revisit the AGI-CFT correspondence, also known as gauge-gravity duality. According to this remarkable equivalence, quantum gravity in a higher dimensional bulk, such as anti-de Sitter AGI space, is fully described by a quantum field theory on its lower dimensional boundary. In simpler terms, all the physics that unfolds in a bulk region can be precisely captured by information on its boundary surface. This boundary acts like a holographic screen, encoding every particle, force, and space-time curvature in a lower dimensional language of quantum states and fields. But how exactly does boundary information translate into the three-dimensional geometry and gravitational dynamics within? The answer lies in quantum entanglement. In the holographic framework, space itself is not fundamental. It emerges dynamically from entanglement patterns of quantum states at the boundary. This realization was crystallized in the Ryu-Takayanagi formula, discovered in 2006. This elegant equation connects the entanglement entropy of a region in the boundary theory to the area of a minimal surface in the bulk. Specifically, the entanglement entropy, a measure of how quantum states in one region are correlated with states elsewhere, is proportional to the area of the minimal bulk surface enclosing that boundary region. The Ryu-Takayanagi formula provides an explicit and quantitative link between geometry and entanglement. It tells us that changes in quantum entanglement at the boundary correspond directly to changes in the geometry of space within the bulk. In other words, geometry emerges from entanglement. This insight reshapes our understanding of space-time. Instead of a fixed stage upon which physics plays out, space becomes a dynamic, emergent entity, woven from threads of quantum information. The fabric of reality itself is not continuous and smooth, but stitched together by entangled quantum states. This deep connection between entanglement and geometry leads to new interpretations of black holes. Traditionally, black holes pose challenging paradoxes, such as the fate of information that falls into them. But holography offers fresh clarity. Black hole entropy, once a purely gravitational mystery, is understood as the entanglement entropy of quantum states on the event horizon. Further, holography suggests black holes might be examples of quantum error-correcting codes. In quantum information theory, error correction protects quantum states by encoding them in entangled states spread across multiple particles. Remarkably, holographic duality shows that gravitational regions, like black hole interiors, can be viewed as protected quantum codes, with boundary states encoding bulk information robustly despite disturbances. Thus, the bulk-boundary relationship mirrors how quantum information scientists construct fault-tolerant quantum memory. Geometry itself acts like a quantum error-correcting code, ensuring information is never lost, only redistributed or encoded differently. This perspective resolves Hawking's information paradox. When information falls into a black hole, it does not vanish. Instead, it becomes intricately encoded in subtle patterns of entanglement on the event horizon. Eventually, as black holes evaporate via Hawking radiation, this entangled quantum information is carried away, ensuring consistency with quantum mechanics. The profound links between holography, geometry, and entanglement extend beyond black holes. They offer insights into the early universe itself. Cosmological holography. Could our expanding universe also be described holographically, with boundary states encoding the evolution of cosmic structures? The answer may lie in generalizing gauge-gravity duality beyond anti-de Sitter spaces. Physicists are actively exploring holographic descriptions of more realistic cosmologies, such as de Sitter spacetimes that describe accelerating expansion. Such cosmic holography remains speculative, yet it suggests tantalizing possibilities. Our observable universe could itself be a holographic projection from quantum states on a distant boundary. In this broader context, entanglement also sheds new light on quantum gravity. The Einstein-Rosen bridge, a theoretical wormhole connecting two black holes, was long considered purely gravitational, but holography shows these bridges can represent entangled quantum states between distant systems. This insight gave rise to a revolutionary concept, EEPR, proposed by Maldacena and Susskind. It equates Einstein-Rosen bridges ER to Einstein-Podolsky-Rosen pairs EPR. Entangled quantum states. In short, space-time wormholes may simply be manifestations of quantum entanglement. Thus, entanglement is not merely a quantum oddity, it forms the foundational fabric of space-time itself. It stitches together distant regions of the universe into a coherent geometry, weaving quantum states into smooth spatial continuities. These holographic insights have profound implications for quantum computing and quantum information science. Quantum information protocols, such as teleportation, quantum computation, and quantum cryptography, can be represented holographically, mapping complex quantum operations onto simpler gravitational analogues. For instance, quantum teleportation, where quantum information moves instantaneously via entanglement, corresponds holographically to traversable wormholes. Such theoretical bridges open potential pathways for applying gravitational insights to quantum technologies, and vice versa. This synergy between holography and quantum information also stimulates new approaches in condensed matter physics. Systems that are strongly entangled, such as quantum critical phases and superconductors, can be described holographically, mapping complex quantum many-body phenomena onto classical gravitational problems. These holographic methods have provided fresh insights into high-temperature superconductivity, quantum chaos, and the nature of quantum phase transitions. Holography thus serves as a powerful theoretical laboratory, enabling physicists to study otherwise inaccessible quantum systems through classical gravitational analogues. Yet, despite remarkable progress, deep questions remain. Precisely how does geometry emerge from quantum entanglement? What mathematical structures underpin this holographic encoding? Can holography fully describe realistic cosmological spacetimes with accelerating expansion? Addressing these questions demands interdisciplinary collaboration, merging quantum information science, gravitational physics, mathematics, and cosmology. Each breakthrough clarifies how quantum information entanglement, coherence, error correction shapes the fundamental architecture of reality. Ultimately, holography suggests a radical shift in our conception of the universe. Space, time, gravity, and matter may not be fundamental building blocks. Instead, they might emerge from more basic quantum information structures. Reality itself could be constructed from entangled quantum states, encoded holographically on lower dimensional boundaries. In pursuing this deeper understanding, we move toward a new scientific paradigm. Instead of seeking fundamental particles or fields, we may soon describe reality in terms of quantum computation, entanglement structures, and quantum error correction. The universe could be fundamentally quantum informational, a hologram crafted from qubits and entanglement. And in unraveling these holographic mysteries, string theory plays an essential role. Its mathematical depth and physical insight provide the strongest framework to explore how geometry, entanglement, and holography intertwine. As we probe deeper, holography and quantum information continue to illuminate our path, guiding us toward a profound unity hidden beneath the complexity of the cosmos. They promise to answer humanity's oldest questions: what is space? What is time? What is reality itself? The answers may lie in the delicate, entangled patterns woven across holographic boundaries, the invisible, quantum threads from which our observable universe emerges. The future of string theory and the quest for quantum gravity. For centuries, humanity has looked outward, peering into the night sky, striving to understand our place in an unfathomably vast cosmos. Yet, as our telescopes gazed ever farther, physics turned inward, searching for deeper unity, more fundamental laws, the subtle threads holding reality together. In that inward quest, string theory stands unique, a framework promising to bridge the chasm between gravity, quantum mechanics, and the profound mysteries at the very edge of understanding. Yet, after decades of exploration, the theory remains both powerful and elusive, offering astonishing insights alongside challenging questions. What, then, does the future hold for string theory? How will it guide our ongoing quest for quantum gravity? the holy grail of modern physics. The journey forward will undoubtedly rely on dual insights from theory and experiment. Theoretical progress will continue to reveal deeper connections within the mathematical foundations of string theory, guiding physicists toward clearer and more testable predictions. Experimentally, advances in particle physics, cosmology, and quantum information science promise new observational probes into the once inaccessible realms of quantum gravity. On the theoretical front, future research will likely explore the landscape of string vacua with unprecedented precision. This landscape, vast as it is, poses a fundamental challenge. How do we select our universe's specific vacuum among countless possibilities? Some physicists argue the solution lies in statistical reasoning, anthropic selection. Our universe's specific properties, such as particle masses, coupling constants, and cosmological parameters, could reflect the conditions that support stable matter, complex chemistry, and ultimately, observers. Yet, this approach raises new questions. How do we rigorously define probabilities in an infinite multiverse? Can we formulate a predictive science grounded in landscape statistics? Future efforts will clarify how string theory can produce sharp, testable predictions rather than merely descriptive frameworks. Alongside landscape studies, theoretical advances will deepen our understanding of dualities, especially holographic dualities like ADA-CFT. As the mathematics of these dualities grow increasingly sophisticated, they promise new windows into strongly coupled quantum systems, both gravitational and non-gravitational. For example, quantum information fluorescence already reveals striking connections between holography and quantum error correction. These connections suggest that quantum gravity may fundamentally be a theory of quantum information. Future theoretical breakthroughs could thus rewrite our conception of space, time, and gravity in informational terms. Indeed, this informational viewpoint may revolutionize our understanding of reality. Rather than thinking of space as fundamental, we may soon regard it as emergent, constructed from quantum entanglement and encoded holographically. Such a paradigm shift would mark one of the greatest transformations in physics history. At the intersection of theory and experiment, quantum gravity research will increasingly leverage cosmological observations. Modern cosmology, with its exquisite precision measurements, provides perhaps our most powerful observational laboratory for string theory. Future surveys of the cosmic microwave background, large-scale structure, and gravitational waves might detect subtle imprints of string-scale physics. Inflationary cosmology, now central to early universe physics, may reveal signatures of string theory through gravitational wave patterns, primordial non-Gaussianicities, or cosmic strings. Cosmological data could constrain the size and shape of extra dimensions, the existence of axions or moduli fields. For example, dark matter candidates arising from string compactifications could leave identifiable signatures in astrophysical or cosmological observations. Meanwhile, particle physics experiments, such as those at the Large Hadron Collider (LHC) and proposed future colliders, will continue probing physics at higher energies. Though direct detection of strings themselves is currently beyond experimental reach, colliders may detect indirect evidence, such as supersymmetric partners, extra-dimensional resonances, or deviations from the standard model predictions predicted by string-motivated models. Precision experiments, probing deviations from Newton's law, or tests of fundamental symmetries offer another avenue. String theories with large extra dimensions or warped geometries predict measurable effects at very short distances, accessible in high-precision tabletop experiments. Moreover, gravitational wave astronomy, still in its infancy, holds enormous potential. Future gravitational wave detectors might observe stochastic backgrounds or signatures from exotic objects such as primordial black holes, cosmic strings, or even higher dimensional gravitational effects stemming from string compactification. Another experimental frontier is quantum technology itself. Quantum computers and simulators are becoming sophisticated enough to simulate strongly coupled quantum systems, precisely those described by gauge gravity duality. Such quantum simulations may soon offer a new way to experimentally test aspects of quantum gravity and holographic dualities. Thus, the future of string theory and quantum gravity will see unprecedented interdisciplinary collaboration. Mathematics, quantum information science, particle physics, cosmology, and quantum technologies will intersect more closely accelerating discoveries and bridging gaps between theory and experiment. As we progress, new theoretical frameworks may emerge that subsume or transcend string theory itself. Already, hints of deeper structures like M-theory, matrix models, or emergent spacetime from quantum entanglement suggest string theory might not be the final step, but rather one chapter in a broader story. These frameworks may better reconcile the conceptual puzzles of quantum gravity, such as the nature of singularities, the information paradox, and the origin of spacetime. Future theories might also clarify why our universe's laws appear so finely tuned for complexity and life. Yet, whatever comes next, string theory's influence will endure. Its mathematical insights, its profound dualities, its deep connections between geometry and quantum physics, these will remain foundational for generations of physicists. In the end, the quest for quantum gravity is more than scientific curiosity. It is a deeply human journey, an endeavor to understand our existence and the fundamental architecture of the universe itself. As we continue exploring, we will surely encounter new mysteries, new paradigms, new revolutions. Each discovery will deepen our awe, expanding our sense of connection to the vast cosmos we inhabit. Ultimately, the future of string theory and quantum gravity is open and vibrant. With each advance, we step closer to answering questions posed since humanity first looked upward. What is space? What is time? Why does the universe exist as it does? These questions, profound, subtle, timeless, will guide physicists through countless theoretical landscapes, experimental frontiers, and philosophical horizons. In pursuing these answers, we may finally glimpse the deepest unity of nature, the ultimate symphony underlying all complexity, the subtle threads from which reality emerges. And perhaps in that glimpse we find our place, not just within a vast, mysterious cosmos, but within a beautifully connected, intimately woven universe, a universe rich in information, entanglement, and possibility. This is the future of string theory and the quest for quantum gravity, not just a search for equations, particles, or dimensions, but a quest for understanding, for unity, for meaning, for the elegant simplicity hidden beneath reality's surface. As we journey onward, string theory will continue illuminating the path toward deeper truths, uniting disparate ideas and inspiring new discoveries, guiding us, ever gently, toward the ultimate theory of everything.